So there's two motivations. From the point of view of the previous two talks, like the previous two talks were about applying Harlow's theorem like vigorously on the boundary safety side. And today I will try to think about what happens if you try to apply it directly in the bulk. Okay. But that was not my motivation for this work. My motivation was I was thinking about like subsystems in in gravity. Because gravity is different of some indirect. Okay. So defining a subregion is a little bit subtle. Like if I can't just use coordinate location or something, I have to define it relational to something. But then if I say, oh, I define this room relative to the the sea, okay. But now I'm defining relative to the sea, which is outside this room, okay. And so if someone comes and messes with where like the gravitational field here between the sea and this room, then the location of my subregion changes, okay, relative to the room, right? Relative to like this chair. So like there's a lot of subtleties in gravitational dressing. But okay, so there are two frames here. One frame is the same frame of the sea. So I say, okay, go to the sea, here is the shoreline, go at this angle, this distance, and now I will find the cube, which is the shore. Okay. And then there is a chair. Okay. And now related to the chair, this room is you go in various directions and there's a cube and that is the room. Okay. Now you imagine that someone comes and like puts a planet between the sea and the sun. Okay. So now the same distance is probably like you'll overshoot wildly. So compared to the chair, the subregion has changed. Even though compared to the sea, it's the same subregion. Right? This is the fact that so you have to be very careful when you dress. If you try to dress a subregion and you end up dressing it by mistake outside the subregion, then someone can mess with the physical content of what's inside your subregion from outside. So it's not a subsystem. Okay, to have a subsystem, we want the same physical degrees of freedom. Okay, no matter what happens outside.
That's because this dressing nature operator is non.
Yes, exactly. That's all the failure. But I'm saying it can be very subtle, and sometimes there can be non-localities that are hard to diagnose. Like it can be that I dressed it to this chair, but then 5 years ago someone defined this chair with respect to the sea. Okay, and then like you and then again the same issue turns up, but then you didn't realize you made the mistake of dressing it outside.
So this is same issue as in gate theory, right? Or is it?
It's different because in gate theory its locations exist. Like
you fix coordinates and then can't be divided.
Huh?
Fix coordinates and then.
So you fix coordinates at classical level, it's enough. But the point of a dressing beyond a gauge fixing is that it allows you to define the same region in different metrics. Okay. So gauge fixing coordinates on a particular manifold allows you to find a subregion in that manifold with that metric manifold. But if somehow the metric changes, you have to say, okay, how do I identify this subregion as a new metric? Okay.
By coordinates like that.
Yeah, but you have to define it.
Then 0x.
No, but then you have to define how you define your coordinate because GR is a generally coordinated variable.
Why can't you say k equal to 0?
Huh?
K equal to 0, whatever the metric, we just say k equal to 0.
That is an example of a dressing. I'm just saying that you have to think carefully about which dressings are good.
Isn't that important? I mean, the k equal to 0 as opposed to order.
Sure, that is one example. I'm saying like I might be interested in what's happening inside that cup, and there is no boundary of that cup with 0 actually. Like then I have to think carefully about how to define what's going on in the cup. Right?
I guess it will become clear. I mean, maybe in the gravitational setup, what do you mean? Can you just draw like a circle with some like, subregion that we usually think of as subregion and then point out as opposed to the C and chair?
But I will just say the same thing with like circles.
Okay, fine. Maybe it will become clearer.
It won't because this is not really, this is just the broad motivation.
Yeah.
Okay. I'm just saying that you have to be very careful in defining subsystems in gravity.
Yes.
Okay.
But
And-
just to, sorry, this is an aside, so you've gone, but is the point that, okay, we can try to define gauge invariant observables, but subsystems have additional.
Yes, exactly. Yeah. That's I think I said those exact words.
Okay.
relational definitions take care of subregions, but a subsystem is something which is more or less isolated, where you shouldn't be able to mess with it from outside.
No, but that's what, I mean, why can't we just say k equal to 0?
That is an example,
Okay.
right? That is an example, but there are other subsystems I'm interested in which may or may not be capable, right?
Fine.
Yeah, I'm just saying that what are the constraints and how approximate are is any given definition of a subsystem and so on. Like there is a sharp question of like filling out these words, right? Which has to be done, which has not been done by the field. Okay, but I won't really get to the point of filling out the words yet. But here I will do some with this motivation in mind. I'll do something interesting. Hopefully interesting. Maybe you decide. Okay.
The subsystem will not change even if the subregion.
Yeah, like or maybe you have to think about like okay, so sometimes I want to think about the coffee in a cup. Then I want subregion and subsystem not to change in relative to the coffee. But then I have to define what the coffee is in a way that's gauge invariant. It gets confusing very fast.
But let me ask the question, I think maybe Chintan had something like this in mind, which is if you allow for a close to classical world, then you should be able to define subsystem.
Well, yes, you should, but I'm just saying that like the rules are not like super easy to understand. Like like the edge cases and so on are not like what is a theory is something that tells you when it breaks down, right? And we don't have like a formal theory of this here, which where you right now you just have to kind of have go case by case, think about what your risk is breaking down. It's not like it's not systematic. Yeah.
Is there something there about the eigenfunctions or what you worried about is something like that where this piece of freedom are the same as that, so you can
No, that's not what I'm worried about right now. My broader motivation is just thinking about what we are doing as what our experimental friends are doing as physicists, right? Like island formula, of course, is I bring up island formula here for a different reason. It is just that we know an example of a subsystem in gravity. It is this entanglement. Okay, it's like you take a state and like you take small excitations around that state. Okay, you get a code surface. It's semi-classical, and we know that there is a subregion which is called the entanglement wedge, which is a subsystem because all the operators there are encoded in a particular part of the boundary. Okay, so there is a known example of a subsystem. So I will start with an investigation of subsystem from what we know up here. Okay. And why, yeah. And I was just mentioning that really this black hole information paradox progress is just like being less dogmatic about what an entanglement wedge is. Okay. That's really it. Okay. And one thing about understanding that entanglement wedges are subsystems, are good subsystems, is that the way we come to it is a little bit roundabout. You use this Euclidean path integral, and it has a saddle point, and that saddle point tells you exactly where you have this region as an entanglement wedge. Well, there is one Lorentzian argument also, which is due to Onkar and Lukovic. Right. Yeah, Onkar and Lukovic, which but in some sense both of these. Right, okay. Mine is slightly different, let me just say. And
What is the Omkar's?
basically they think about in a case when you have a U1 symmetry in the boundary replica path integral, we know the answer because of Cassini-Myers, and they build up a perturbation theory about where the boundary of the entanglement wedge goes, and you can like iterate this perturbation theory to look at finitely far away states. Right?
Yeah.
And I believe they're working on the quantum extension now. Yeah. But anyway, I will try to think at the level of like algebras and gauge invariant operators.
What exactly is the question that you are trying to understand in the Lorentzian way?
So deriving the HRT formula.
deriving in full without any assumptions or what?
There will be different assumptions, but in a Lorentzian manner. So the current derivation of the HRT formula, okay, the best one is a replica trick for Euclidean path integral based derivation. But the point about Euclidean path integral is that it hides the Hamiltonian structure. It hides the Hilbert space structure of it. Okay, in some very weird ways. And so trying to understand it from a purely Lorentzian perspective is interesting to improve our understanding of this problem.
But I'm so sorry, please forgive me, but I mean, for a time dependent situation, is there an honest to goodness derivation of the HRT formula? Because you may not be able to utilize this. I mean, some time.
For states prepared by Lorentzian path, like for states prepared by Euclidean plus Lorentzian path integrals, I think Dong Lukowicz or Rangamani is a derivation. Yeah, I with like some reasonable assumptions. And then Dong Lukowicz included the quantum correction.
But how do they do it? As Sandeep said, how do you, so you have to go to Euclidean at some point.
Yeah, I think
Yeah.
So how do you go when you realize?
do time codes and stuff like that.
Yeah, right.
So you have to do it with complex geometry.
Complex job. I mean, you have.
But sort of minimally complex. They kind of think about contours that are, where the lapse is real for some parts and imaginary for other parts. No weird complex lapses.
But for an arbitrarily time dependent profile on the boundary, it seems quite challenging. Right?
Yeah, I think they only consider things where you can make it via boundary path. Which, yeah. Which is,
I mean, it's true. I think it must be true. But
Yeah.
it's-
Yeah.
There are some arguments that path integral states are dense in the Hilbert space, but I've never found a good reference for this like clear argument.
In the Lorentzian way, if you want to derive it, how do you start?
Okay,
I mean, what you want to write down is an entanglement entropy, right?
yeah.
So that usually is defined in this replica way.
But I would refer you to Parikar and Yukovic and also upcoming work by Parikar and Yukovic.
See, what we do is, we take as a starting point the U1 symmetric case. So you imagine that you have a U1 symmetric.
Okay, and there you assume that the formula is correct.
There you assume that the formula is
I
correct.
think
because
Cassini what more
Cassini
than proof, yeah.
Cassini-Werther Myers have explained that.
In Lorentzian way. But why do you say Cassini? That's Lukowicz Martinez will take care of all that if you go to Euclidean, right?
I mean, Lukowicz takes care of all cases.
No, but the point is that you want to understand in Lorentzian way.
Yes. So
Yes.
you take that as a starting case.
Yes.
You assume that we believe the Ryu-Takayanagi formula, that's U1 symmetric case. And then you imagine starting to perturb away from that. Now that perturbation doesn't have to be small, as long as your final state is connected in some way to the U1 symmetric case by small perturbations at every step. Then at every step you show that if the Ryu-Takayanagi formula was correct at this step, then it would be correct at the next step. You keep building that. That goes beyond.
But now this U1 symmetry is the one that gets broken to Zn under the
Yes.
replica.
Yeah.
But if for a general time dependent case, you won't have that, right?
The boundary path integral will have
But
that.
your point is if you can build up the general time dependence in a sequence, that's very interesting.
That's and at every step, anyway, I don't know.
No, it is good.
Anyway, at every stage of that calculation, you just have to resort to Lorentzian techniques, right? Because even though the entropy is a nonlinear object, changes in entropy.
Yeah. And I will take a very different tack where I will not prove I won't actually get to proving the HRT formula, but I will prove a slightly different shape.
Using some more substantial things.
No, the less of it. You'll see.
Okay.
Then let me get to the statement. But let me just first remind everyone what the statement is that the entanglement entropy of a boundary subregion capital B in a boundary state capital psi, okay, is given by like some extremization and minimization problem of the area plus bulk entanglement entropy. Where little b here is there is a surface capital X which is homologous to capital B, by which I mean that there is a bulk region little b bounded by X and B. Okay, so like these are some examples. And the
You said extremization minimize, but isn't it min and max like on space?
so extremization can be thought of as a maximal. But I won't care about the maximum. Just okay. It's like you get extremized, you get a discrete set of solutions and you minimize them. Oh well. Maximum is a continuous thing. Okay. What the important thing about this
Sorry, by moving in time, you can become smaller, right?
yeah. So that's why the extremization.
Right,
And
This-
this
one is different. This is over multiple sources.
Like for example,
okay.
if you have the
So you do the min max and then among them all you choose them.
yeah.
Thank you.
Yeah. Anyway, so the important thing about this formula is the following. First of all, that this bulk subregion little b is not something that you'll get to choose. Something that gravity chooses. Okay. This is a very big difference from Harlow's setup where the sort of bulk subregion, the code subregion was fixed in advance. Okay. And as most of you have probably heard, this bulk subregion, all operators, EFT operators in that bulk subregion can be expressed as operators in the boundary subregion capital. This is called entanglement by reconstruction. Okay. So what I will do is the following. Okay, I will consider what sort of regions can be bulk duals to boundary subregions. Okay, so let it be in the previous case, the entanglement wedge is the boundary boundary subregion dual to the bulk subregion. The entanglement wedge is the bulk subregion dual to the boundary subregion. Okay. So now.
So by dual, we mean
Every operator that can be reconstructed here. Yeah. And I will give a very precise definition of a dual of subregion duality.
Just to understand, is there some implied notion that every light operator or what you might call in the code subscript in little b can be reconstructed?
Exactly.
Because if you take if once you start including back reaction, everything moves around, and
That's
also
true.
there's the sense in which it's
That's true.
code light operators.
That's true. Okay. So what I will do is the following. Okay, I will think about what sort of bulk subregions can be dual to boundary subregions. Okay. So here are two boundary subregions, capital B and capital B. Right? Okay. And in green, I have shaded the what are called the causal wedges. These are the set of points that are causally accessible from P or P. Okay. Now, suppose someone comes and claims to you, okay, the bulk subregion dual to capital B is this little b here, the shaded thing. Okay. What do you say? Yeah. First of all, how will you go about checking this claim? First thing you will claim is that everything in the causal wedge can be reconstructed in B just by equations of motion. So the causal wedge of capital B better be little b. The causal wedge of capital B better be little b. Okay, this is the first check. So this is the second check, which is the new thing I am.
Sorry. So everything in green can be reconstructed by B.
Yeah.
And then, but B seems bigger.
Yeah.
The wedge of B seems bigger.
Yeah.
And then what did you say?
So I'm just saying that first check, if someone gave you a little b that was like inside the green region,
Inside.
then you would immediately know they were lying, right? Because obviously there is a bigger, there are regions if little b ended here, then there would be all operators here. You could reconstruct and get here.
Oh, little b by definition is what cannot be.
No, little b is something someone handed to you.
Okay.
And they're claiming that little b is dual to capital B.
Dual to capital.
Okay. And what do you say? You want to check the claim. Okay. You can imagine this. I am the one handing it to you, and you know I lie a lot. So.
But what was the statement? Sorry, so someone hands little b to you. If little b is inside green, but not all of green, you know immediately they're wrong.
Yeah.
Okay, yes, that.
Now, what are other checks? Okay, and the claim is, and the idea is the following: that it is possible for you to act with a bulk unitary in the complementary bulk subregion, little b bar, okay, which basically makes the edge of little b causally related to capital B. Okay, so here I'm using coordinates where this point is fixed, so it looks like a boundary subregion is moving because actually the relative location of this and the boundary subregion. So in principle,
I'm not quite understanding the logic again. Can you repeat that? So you are.
so someone handed you this little bit.
Yes.
You want to check whether it can plausibly be the dual of capital B.
Okay.
Okay. It's important here that everything in little b is space like separated to capital B.
Capital B bar is its complement on the boundary.
Yeah, it's
complement
a
of
boundary
B on the
complement. Yeah, good. All big bars are complements.
Okay.
Okay, yeah, sorry. So capital B bar is the complement of capital B. And it's important that everything in little b is space like to capital B bar. Okay, because clearly everything in capital B and capital B bar commute. Right? And if little b and capital B bar were timeline separated, then they would not commute, which means an operator here cannot be an operator here. Now the point is, if I can act to the unitary in little b bar, which makes little b and capital B bar timeline separated, then little b cannot be the bulk separated one. Because an operator here now commutes with the an operator here conjugated by this u prime. Okay. Therefore this cannot be an operator here. Okay, that's the main idea of this one. Okay, and this is based on like some things that happened in 2019-20, like that's where the idea came from. So yeah, so the main argument is that first of all, if it is possible for such a unity to exist, then little b cannot be the bulk subregion dual of capital B. Okay, otherwise you would have contradiction with boundary causality. Boundary causality states that capital B and capital B bar are commuting, just space like subregion. Okay, and then I will take a specific system JT gravity plus CFT and prove that such a U prime exists, which makes these two come into causal contact unless this point is an extremal surface. Okay, so that tells you that this one consistency condition reduces the set of possible bulk duals to extremal surfaces. Okay, it's like otherwise there could be like infinite without the consistency conditions. There are like infinite number of wedges sort of written down that look like good candidates. But with this consistency condition, there's like a finite set.
Just to understand, this is possible unless B lies to the left of the QES, right? That's what you mean. That is, QES is the boundary of the region where this is
it's a
possible.
little bit okay. That's not exactly the thing, but there is a sense in which that is true. But it doesn't. Okay, I'll be more specific.
Okay.
Yeah.
Because I mean, you won't be able to.
I will be more specific. Yeah.
Just so that, just so that I understand it. So you are saying that there is only one point, only one point in this space time, which if you let's say there exists some B bar, you act it with some unitary, and there is just one point which will not commute with it.
There's just one possible point here.
Yeah.
Like out of all possible points, there's just like a discrete set of points which are the QESs, such that this B bar will never leave this guy will never leave this little B bar.
Come in contact with the light pool. This-
Yeah, it will never come in contact with the right one. Okay. Otherwise, if it's not, then it's possible for it to come in contact. And I will be more specific about the real statement. Like this is not quite the full statement as Sanjay pointed out, but I'll be more specific soon.
So from these 2 points, we are saying that entanglement with the instruction is possible between the quantum extremal surface and the point.
These are the only candidates. I will say that these are the only possible candidates for bulk duals. Now, whether any of these candidates is realized requires some further thought. Okay, which I will comment on maybe at the end if there is time. Okay.
The unitaries come from inside the green on the right.
The unitaries live on little b bar. Okay. So they have to commute with the EFT operators in it.
Higher dimension also you will be able to say.
There is a student working on it, and I have the structure of the proof, but I'm hoping the student will fill out.
And this statement is only valid if you have two CFTs, B and B bar. What if you just have
Like if for any two boundary subregions, this is fine. If B and B bar are like different subregions of the boundary CFT, this is kind of some weird coordinate system. You can think of it that way. Like what I'm saying here doesn't depend on the shape of the boundary subregion. It's just like I'm drawing it in a particular way.
See, in higher dimensions, you can carve out a region deep inside the bulk using piecewise extremal surfaces, right?
Uh-huh.
So that also would be a candidate, you think?
It has to be homologous to capital B.
I don't know what capital B, right? I'm handing you the small.
No, you also have to hand me capital B. Because
I thought your
capital B bar is
I thought your conclusion is what bulk duals.
Oh, capital B are allowed.
No, I thought you.
I'm
Sorry, your conclusion is that what sort of bulk subregion can be dual to a
capital B.
yeah. It's
So
not
capital-
specified, right? Some
Capital for a given capital.
for a given capital.
Because see, and the important fact contradiction would be that capital B bar is in causal contact with little b.
I thought you were saying
Capital
for
given-
any choice of B, this something like that. No.
For a given capital B, little b has to be spaceless separate from B bar even after the action of all unitaries. Okay, this statement is true for all capital B or capital B as an input into the statement.
No, but your conclusion is that the small b has to be extremal, right?
The boundary of small b has to be.
Yeah, the boundary has small b, but it doesn't mention anything about capital B.
Well,
You made a statement which is independent of capital B.
And you
When you
are
say that
there is no homology condition.
Yeah, there is a homology condition. Like for given a capital B, its bulk dual can only be extremal.
No, I think
What
the
do you
question, maybe the question is, okay, so you say that the boundary of B has to be extremal.
Yeah.
But it also has to be homologous to.
Yeah, of course,
So
yeah.
that is also part of your proof? or-
Yeah, that is important. Yes, it has to be
Are you
homologous.
assuming?
I'm assuming homologous.
Yes.
Yeah.
but I thought
Otherwise, you don't get anything like sufficient duality.
I thought when you put out, I mean, this would be also a meaningful statement, right? Maybe that's not what you're making, but that let's say I draw some wiggly region on the boundary. K equal to 2 bound, K equal to 2 surface,
In the bulk.
right? Is the bulk. And then you will say, no, this just cannot be.
And this cannot be the
There cannot be any capital B such that this is doable.
first of all, it is not homologous to some boundary region.
It is
Obviously.
homologous, let's say, but it's not extremal.
Then it cannot be dual to the boundary region. It is homologous.
Yeah. Anyone, you know.
Yeah.
But I see.
Because even a surface, bulk surface, there is a homologous surface with boundary. Unless you're like inside a razor or something, but you can. Okay.
Whether is this complement of B?
Yeah, all bars to complement. So like a bar on a small letter means bulk complement, bar on a big letter means boundary complement. Right.
But now I understand, is the statement better? You're saying the only regions which
Can for.
Huh?
Yeah, go ahead.
which cannot be brought into causal contact with, given a B, the only regions which cannot be brought into causal contact with some B bar
Uh-huh.
are such that they are bounded by a quantum experience.
Yeah.
That's the state.
Yeah.
Okay, yeah, okay.
Yeah. So let me just. Are there more questions about this slide? You guys want to? It's okay. You can. Yes.
For a pure state, this statement, is it an obvious statement? Because the QAS will be same for B and B bar.
Yeah.
So the causal wedge of B bar should be smaller than.
Yeah. The causal wedge should be, but the new thing here is that I'm allowing this. Like that is the obvious statement here. Okay, but the new thing is that I'm considering the statement after the action of this bulk unit. Okay, so I'm allowed to move the like this bulk unities can change the relative location of the causal wedge and this surface.
Can I just draw something?
Yes, please.
So if I have stick to the matrix.
It is a dark draw, no?
Chalk. And now let's say my bulk region, small b, this one. Okay, both are extremal. Okay,
But
And
it's not
this-
extremal everywhere.
and not everywhere. That's why I was asking piecewise extremal. So in this case, this boundary, apart from this point, would be extremal, and this would be homologous to this.
Yep.
Right, but it's not true that this stuff is dual to this, right?
Yeah,
Because dual to this, we know what is. It's this.
yeah.
Not this part here.
Yeah.
So you want to use this.
I have only a sketch of the proof in higher dimension.
Yeah, I was just wondering whether one can use your results to make more regions. This is also, except at one point, it is extremal, right?
Yeah, but I believe that my proof sketch in higher dimensions is like works point by point.
Okay.
But like it needs every point to be extremal. But there could be some
Maybe
subtleties
in a
that
little way which one can quantify and then get a new sort of reconstruction.
yeah, and you're obviously coming from the soap film perspective.
Not really, but yeah.
No, that would be interesting if one could say something like that. I agree. But I do not know. I mean, currently high dimensions is a sketch, so everything here is 20 right? Huh?
You said that diagnostic for failure is like capital B bar coming in contact with small b.
Yeah.
It's not enough for some other subregion small b bar to be in contact with small b.
Because capital B bar is the set of things is to commute to capital B. That right green guy has to commute to everything in capital B. So if something doesn't commute to the right green guy, we know it cannot be in capital B.
That I get it, but like if I just say small b comes in contact with some subregion in small b bar, that itself doesn't give you.
It's not as sharp a statement. I'm using causal wedge reconstruction to make it very
So
sharp.
something non-extremal would go through that if I just demanded that. If I just demanded some subregion in small b bar comes in contact with small b under action of a right allowed unit.
Wait, for a difference,
Would go through. Like this.
maybe I'm not entirely sure. I have to, but I'm just saying the starting point is not like sharp. So I can't. That's why I haven't thought about it. Yeah. Okay. So this is a basic idea. More precise statements will follow. And okay. So now let me just give you some notation. All boundary quantities are capital letters and all bulk quantities are small letters. Okay. So there are subregions, algebras, states, and unitaries. Okay. And always a big bar on the on a region means a complement, and a prime on an algebra means the commutant, which is the set of operators that commute to it. Okay, and ADS-CFT for me will be that the boundary state will be dual to bulk metric and the state of the bulk in the bulk. Okay, and I'll also use this notation WCB G side to denote the causal wedge. Okay, so C means causal, of course, and the causal wedge depends on the boundary subregion, so B. But it does not depend on the full state, it only depends on the bulk metric because defined by causal relations in a metric. So it only depends on G side, not on psi, not on the other information in the boundary. Okay.
So this B bar, the complement of some subregion B, which is B bar, it's not necessary that it will commute with
capital B. It will. It has to. So the idea is that suppose you have some QFT, okay, and this is B. Okay, for me B is like it's like a causal diamond. It's every operator here can be Heisenberg evolved to this subregion, this interval. Then you consider all points that are space-like subregions on capital B, and that is B plus.
But I thought complement of this B is all that is not B, right?
No, everything is space-like subregion. Okay, good. Sorry, I should have. So for me, complements always have space-like separated regions. The set of space-like separated regions. Okay? Yeah. So yeah, because an operator up here is actually can be written as like in terms of operators in B and B bar. So like together B and B bar generate the whole element. Okay? Cool. So now let me give you some more careful introduction to subregion duality. So we've been through this slide before, so I'll just skip it. So the point is that when we think about, as I mentioned in the slide with the picture, I will care a lot about things that backreact. Okay. So now I want a language for subregion duality. Okay, which is robust to backreaction. Okay, and the right language is what is called state-specific product unitary reconstruction. I don't. Maybe it should have been a product unitary. Anyway, state-specific product unitary reconstruction. Okay. What this is that suppose you have a bulk unitary, and it's a bulk unitary, not some other object. Okay. Then that bulk unitary acting on capital psi. So a bulk operator acting on a boundary state means that I act with that guy and take into account his backreaction. So okay. A more the authors of these papers will put a holographic map here, but I can't be I don't want to clutter things up. That acting on a boundary state psi is bulk unitary is this gives you the same state as acting with some particular boundary unitary. You capital. Okay, this is subregion duality. This is reconstruction. It depends on the state. Okay, and this is quite important because when you do this, you're not demanding that your set of reconstructible operators forms an algebra. Okay, it is not loaded under addition and multiplication. For example, if you take an operator that creates a small lump, act with it a number of times, that is 1 by g Newton. Okay, then the mass of the lump will become like 1 over g Newton and it will become a black hole. And then the background will completely change. All the information you put in will go behind the horizon, and you don't want to deal with that. So you just say, okay, when you put the u to a large enough power, that is not reconstructed on this state. That's it.
That is why need a backreaction?
So this is backreaction. The fact that relative locations of points are changing due to the insertion of a bulk operators, that is what is called backreaction. Like the energy of this guy will change the geometry of the boundary of the bulk.
But the thing somehow will feel some order of G Newton was.
Yeah, if the bulk unitary actor will had order 1 by G Newton energy, then like some very, very drastic thing will happen. And you don't want to deal with drastic things. Okay, like you're just taking like it's a perturbative change. That's what I'm thinking about. Perturbative in an appropriate sense, not. But like it's not like creating a black hole or adding a wormhole. I don't want to deal with all that stuff.
Is it fair to say your bulk FTS?
My bulk FTS? In this talk, no, it's JT gravity, so there won't be. Yeah, but I think what I'm saying, I have a sketch for what to do with when there are gravitons and so on, right? But I haven't made it precise. So
I understood that situation, or what do you mean by taking account backreaction of graviton?
Yeah.
No, but you have
Gravitons and also the Coulomb mode also is part of that.
you have matter. Yes.
I have matter, but I don't have gravitons.
Yeah, I understand. But you take into account presumably the back reaction to matter.
Yeah, that's exactly what I mean.
So that's like the
It's a Coulombic mode. Yeah.
Usually reconstruction one uses, is for general operators, right?
Yeah.
Here you are just going to use unitary.
Yeah, here it's only unitaries. Otherwise, you can get into trouble with backreaction of non-unitary operators is very funny. Okay. Yeah.
So your statement is what which bulk then can be dual to boundary region.
Yeah.
Dual meaning reconstructed in the reconstructed sense.
Yes.
Right, in that sense.
In
So
this
your requirement is weaker than reconstructibility of the full operator.
Yeah.
I mean, then just you use the unitary.
Yes.
Okay.
Exactly. The set of reconstructible operators will not form an algebra.
Yeah, not just that, but you just look at unitary.
Yeah.
But I had something similar to ask, which is usually we believe that everything which lies within the entanglement wedge in the bulk forms. I mean, the light operators or gravitons form the whole subspace. Right? So,
Yeah.
so any operator acting on the code subspace can be pushed to the boundary which reconstructs it, right?
Yeah.
As you were saying.
Yeah.
So why not, I mean, there's something special about the unitaries which makes you.
So in QFT, right? There is a famous Reed-Leader theorem, which says that if I act with non-unitary operators here, I can create an elephant on the moon. Okay. Non-unitary operators mess with bulk locality. Right? And you don't want to like and because we are talking about quantum extremal surfaces,
Okay.
you mess with bulk locality can change the entanglement structure and like, so you what do you say? We talk about algebras, but algebras are more of a crutch in all of this, that really you should only be in the unitary. Because algebras have a nice beautiful structure, which sets of operators do, sets of unitary operators do.
Yes, that's.
Thank you.
This unity which means P and V bar is contact, is it also clear that it creates a negative stress tensor or something?
It will create a negative stress tensor. Yeah, it was the thing that was used in proving to. Okay.
I'm so sorry, this little u is a loop.
It should be local. It should be well localized. Yeah.
Sorry.
Right now, I'm not talked about subregion duality. I'm just talking about reconstruction yet. But yeah, it will be little bit. Yeah, but good. Okay. The other reason, by the way, the state specific thing is important is that you can have different reconstructions in psi and some other state in tilde psi. Okay, so for example, if you and here consider suppose you were like something which created an excitation in a particular mode of the free field. Okay, in global ADS. Okay, and u tilde was an operator that changed the geometry of global ADS. With the same operator, you will not create a single mode excitation anymore. Right? So it had to be a different operator on the boundary. And so this language also allows for this subtlety. So back reaction, basically back reaction of u tilde might like just change the reconstruction, and that is fine for us. Again, Harlow's theorem, which has exact error correction, does not allow this. Okay.
Second, Harlow's theorem doesn't allow what, sorry?
For there to be different reconstructions on different states in the course of this.
Oh, I see.
Because of exact error correction. This is something that turns up in an approximate error correction.
So you have two different states in the same subspace.
Yeah.
And then, you expect there is some given whatever isometry map and all that, but you say here you have two different bulks.
Yeah, here it's two different reconstructions, and that is fine.
But in the bulk, I mean, the way I understand, just to ask you all is, okay, Harlow, everything is when you are neglecting back reaction.
Yes, exactly.
Right? To that extent, you keep the reconstruction path the same. Right?
Yeah.
Here, what you're saying is once you include the back reaction, it can change.
Yeah, exactly.
So in a sense, you're trying to go beyond.
This is exactly.
I mean, from your point of view, you need to because
I care about back reaction. Okay.
No, but in Harlow's theorem, there was not necessarily any talk of back reaction, right? Just a QIC theorem.
It was a
You could change, as you said, this P alphas. So that is kind of like
that's like a very, very crude back reaction.
very, very, strong. Changing the mass of the black hole, right?
But
that was still allowed, but
okay, as a QI theorem, I see what you mean, but when we applied it to the bulk and we said, okay, this is
it is what Abhi is saying is right. That Harlow's thing is the most like clearly applied to like black holes to coarse surface arranged with black holes of different masses. But the bulk operators in that coarse surface never change the geometry of each black hole. It's always like a set of black holes. Okay. Well, I care about like bulk operators that change the local geometry, not just one global mode. Okay.
Once you start including back reaction, you don't even know what the region is, right? Because it changes the response to. There's
a limit that one has
so
to.
you cannot complete the whole story.
Yeah, so I'll try to convince you that there is a good set of limits where like the some state central state will come out. Okay, cool. So now let's this was a global statement of reconstruction. Now let us define subregion duality carefully. So consider pure state on B union B bar. So, the P and P bar are two space-like separated regions which together form the entire quotient, cover the entire quotient space of the boundary theory. Okay, which defines something called the max EW. Okay, now usually EW stands for entanglement wedge, which is the wedge bounded by a QES. But today I'll just use the word EW to mean whatever's on the slide, max EW to mean whatever's on the slide. Okay, and I'll prove the QES of it later. Okay, so max EW, which I will denote by WE, depends on the boundary subregion and on the boundary state, is the largest bulk subregion satisfying a certain condition. Yeah. For a set of simple local unities in this max EW. Okay.
Just 1 minute for context.
Okay, good. So I am trying to.
Sorry,
Yeah.
Doctor had to take.
No, yeah. Okay.
So sorry that
Yes.
I thought it would be over by now. Yes.
Yeah.
Doctors have no time.
Okay. So good. So what I'm trying to do is I'm trying to think about subregion duality in ADS-CFT from like purely Lorentzian perspective, and I'm going to give a consistency condition that says that the bulk subregion dual to a boundary subregion in a particular in JT relative to CFT has to be bounded by an extremal surface. Okay. So let me just.
So bounded means less than equality or
has to be the subregion, the boundary of the subregion has to be an extremal surface.
has to be an extremal. Right.
Yeah. Okay. So now let me just go back one slide and so that you'll see the idea come up slowly. Wait. So what is I'm first right now I'm at the stage of defining what subregion duality is.
Maybe Ronak, that first slide with the B bar and B bar.
I thought maybe let him see it slow. Okay. Yeah. I was thinking of going back, but yeah. Okay. So for me, subregion duality is sorry. So capital psi here is a boundary state, and little u is a bulk unit. Okay. A reconstruction, like I will define only state specific reconstruction, which means that acting on a given boundary state, there is and a given a bulk unitary and a given boundary state, there is a boundary unitary satisfying this equation. Okay. This is the right notion of reconstruction if you want to keep back reaction around in your life. Okay, because it does not demand that the set of unitaries forms an algebra. Okay, which is fine because any unitary you have put enough time to make a black hole. Okay. Secondly, your non-unitary operators acting on a acting like mess with bulk locality, and you don't want to deal with that also. That's why it's locally unitaries. Okay, so reconstruction is called state specific. Okay, for the boundary operator, reconstructing a bulk operator depends on the boundary bulk unitary and also the boundary state.
But how state specific? In the sense that you now, you unsize some other state now.
Mm-hmm.
So if you did it, I mean, it should be like neighborhood specific, right? Or not?
Yeah. In the end, it will be more or less neighborhood specific, but I won't need to impose that. State specific will be enough for me.
Okay.
So neighborhood specific is a special example of state.
It's more general than state specific. But neighborhood, what I mean is that
Neighborhood specific is like more constrained, right?
More constrained. Yeah.
So this is more general.
Yeah.
How does it take care of that reaction?
Because a nice example is like consider so suppose you have global areas, okay? You creates a particular single excites a particular mode of global areas. Okay, so suppose that's what it does. Now consider a different unitary u tilde, which wiggles the geometry of global areas. Okay, so now u tilde as such, when you take it out back reaction, has a slightly different geometry. So now the same operator u won't excite one mode, it will excite many modes. Okay, because exciting one mode is something very specific to geometry. You have to use the solutions, the equations of motion, and so on. So that means that in terms of the boundary operators, acting on u tilde side, you'll have to put many modes here. Acting on just psi, you'll have to put just one mode here.
Sorry, the fact that this equation is only supposed to be true on that state.
Yeah.
So it's a very weak condition then, right? Because you could have.
Quite weak, yeah.
Yes. Okay.
Yeah, and yeah.
Because its action on any other orthogonal state could be absolutely any. Could be non-unitary. Any-
No, I want it to be unit.
Okay, you demand, right?
Yeah, sure. Everything is unit. But yeah, it could be any unit.
Yeah.
Some non-crazy unit, yeah.
Okay.
Okay. Okay, good. So now let me just, that was just reconstruction. Now I'll talk about reconstruction of subregions. Okay. So, again to repeat, we have a pure boundary state, capital Psi on capital B and capital B bar. Okay. And I define something called the max EW. Okay. Which is the largest bulk subregion. Such that, suppose you give for any simple local unity, where simple has not defined. Okay. There is a unitary reconstructing boundary unitary reconstructing the simple local unitary. But you are allowed to activate any unitary bulk unitary in the complement of the max CW before you do the reconstruction. It's the same capital unitary, and this is a slightly stronger statement now. The same capital unitary regardless of what's happening in the complement. Okay, this basically tells you that that the complement has no effect on what's happening in your bulk subregion. Okay. Yeah, and by simple, I will mean low energy and local bulk units. That
So now this is the neighborhood kind of condition. When
It's
neighborhood states are obtained from psi by this
Yeah.
WE.
exactly, but it's not the obvious neighborhood condition. I'm not thinking about it in close in some one norm or something.
Don't even know what that means. Okay, fine.
Like I'm not saying that it's the same if psi and psi prime are psi minus psi prime.
Fine,
Yeah,
yeah,
yeah.
fine, fine.
It's the neighborhood condition depends on the subregion.
Yeah.
Okay, and it's the largest per subregion. Okay, so like for example, the causal bridge satisfies it. But if you have little u at the causal bridge, as long as u prime is space-like subregion, doesn't affect the causal bridge, then the HKL unitary will do the job. But it is not the largest such. In general, there might be larger ones. Okay.
I'm sorry, what is the? Yeah, U prime belongs to A prime, what is A prime?
Good. So thank you. WE psi is the bulk region.
Yes.
WE psi is the algebra of operators in that bulk region. A prime, putting the prime means I'm looking at the commutator. So it is the algebra. Suppose this is the bulk region. I'm looking at all operators supported here, including dressing. So dressing is not allowed to leak into my region. Okay. So that means that little u and little u prime commute up to exponentially small dimension. Okay, if the dressing is formed in the correct way. Okay, and yeah. So this is my notion of this thing. So what's important here is that little u, I am saying it's a low energy local unity. It does not backreact.
What is little u prime of the right side?
It's the same little u.
So it's still a bulk.
It's still a bulk.
But it's valued in the commutator.
Yeah, exactly.
It's for any U prime valid in the commutator.
Exactly.
You could have written it as capital U prime also.
No.
No?
Because here I'm not assuming computator.
Just one second.
Yeah, it may not be that little u prime is in the boundary. In particular, another reason, even if I assume complementary recovery, there is no restriction on little u prime. It can have huge backreaction. Little u, because the low energy local bulk unity, won't have high backreaction. Little u prime, no such restriction. Okay, because little u prime is an adversarial object. Okay, little u is the thing that is the sort of approximate Coulter space. But little u prime is like the thing trying to mess with your Coulter space.
So that's the one that you're going to use to make the capital B prime.
Yeah, exactly.
So this is the statement that if I act on outside my region, that does not interfere with the implementation of the local bulk operator in.
Yes.
Okay.
Yeah.
I mistook it first. Okay, thank you.
This is exactly that.
Could you explain the second last diagram?
This paper, this one?
Yeah.
It's not important. This is about like these papers were about like just some tensor networks and so on. So I'm just saying that they have a very, very specific notion of what little u means, what simple means, okay, which is much more precise. I am just going to fudge it to anything which doesn't.
And so your definition of simple is just that.
Topology, local multipliers.
So if you're going to include arbitrary amounts of back reaction in the U primes, I mean, you understand the notion of the bulk Hilbert space and unitaries and all that well enough to claim that there is a algebra localized in some region in the bulk and a commute out.
Okay, good. So
I'm just asking.
this is a great point. And so if you open the paper, I will say some very careful words about this. That this algebra is an algebra of the bulk PFT. Okay, and which does not this algebraic structure does not include back reaction. If the back reaction comes only when you act on the boundary state. So anyway, we can discuss this maybe later, but there is a sort of annoying set of words I can use to make this algebra statement, right? But in practice, what it means is that you consider unitaries on the complement so that the tracing does not leak into your region. Okay, this is crucial. The tracing cannot leak. If it leaks in, this statement need not be true. Okay. So this was the okay, good.
So since U is simple, you can't include U and it's regular.
Yes.
A prime can.
U prime can do clearly. Okay.
And this B and B bar can be arbitrarily smaller, large.
Capital B, capital B. Yeah, that's an input into the question, right? Because you want a bulk dual to capital B. Right, so it's an input into your question. So okay, you can take a small capital B and then you get a small bulk dual. That's fine.
So U prime psi, I should think of from the bulk point of view as a metric which has these two wedges. One wedge which is the same as that of psi.
Yeah.
The other wedge which is messed up.
Yeah, exactly.
But they have some condition on the
Yeah.
Where they are trying.
Yeah.
Some is relevant.
Yeah, there's a co-dimensional 2 version of word. Yeah, that's exactly.
And these wedges, the left-hand side is the messed up.
Messed up, right? But this is
Actually, I think for me the right will be messed up.
Oh,
But
whatever.
okay.
Can such solutions here, the solutions which are the same here and then change there?
Yeah, you can write you can do it. I will construct in.
Or maybe that's the point. Maybe that requires your thing to be extremal.
No, that's not what it was, but let's get through.
We're just repeating Sandeep's question. Is this going to be a large n kind of thing or more than that?
It's a weird thing where I'm keeping G Newton finite, but like not so finite to include like a non-perturbative corrections.
So you're saying large n and all orders in perturbation theory?
Yeah, I think so. But where the perturbation parameter can compete with one, it's not a formal perturbation theory.
But then why aren't you including non-perturbative corrections?
Yeah, it's a funny limit. I'm not sure. Like I think this is relevant in like it turns up in like concrete calculations. This thing where you consider perturbative back reaction to like build up, but not consider non-perturbative corrections. And yeah, I agree. It's not like formally well defined.
But if you know any order in perturbation theory, there is a way to get non-perturbative.
I mean, in some cases you can use Borel summation, but that doesn't always work, and also like it's just hard.
So Ronak, if you look at the metric on a space of lines as function of coordinates, let's say, that should be an analytic function, right?
Right. It should be typically people put a C infinity condition, which is not
Yeah.
analytic.
Okay,
It
so
much weaker than analytic.
Okay, so that is allowed for this freedom.
Yeah,
Cannot
I
easily
will.
continue outside. If I know a metric in some region, I would always thought that the
No.
differential equations will fix.
No, the constraints don't really require you to. In fact, my metric will be C1, but the constraints seem to allow that.
Why your matrix are C1? I mean, metric shouldn't have discontinuity.
C2.
But even
It's not
any
different.
higher derivative, it should not break down, right? Should
Oh.
be C infinity.
I think good. So you should think of what I will do as like a leading order thing where I have like very well localized shocks, but impact of the shock should be a bit spread out, in which case I will get many more derivatives. Yeah. Cool. Okay. So now let me translate this statement into consistency condition. Right? And again, entanglement wedge for me, yeah, I chose bad naming convention, but entanglement wedge for me is not the region bounded by QES, it is the bulk subregion defined by this. Okay. So the first
Sorry, one more. I mean, if you act with enough U primes, you can also excite the gluons. So that's also allowed. It's like not just large non-perturbative geometric corrections, but crazy things, creating black holes and so on. That's also allowed or not?
I would say that in this thing I am getting U prime should be a EFT unitary which backreacts.
So basically large classical back reactions in geometry, but not more than that.
Yeah, I think that's I also for higher dimensions actually I need that also. But anyway, there's a student I want to work on. I'm hoping will work
Is there
on
a
it.
clear way to make that distinction? Back reaction and everything, backwards also, same type of back reaction. What is the?
No, like you can define a EFT algebra. Okay, U prime should be within that EFT algebra.
You can make backwards with the EFT algebra, right? Full algebra. Just use a lot of.
Yeah, true. Yeah, I think I suspect that this won't really matter. The certainty won't matter, but yeah, I should think more carefully about it.
I mean, the point is, I think that in whatever calculations you're doing, you should not have one. You know, you can have other wormholes distributing everything on Euclidean algebra. There's at least one Euclidean algebra, maybe one algebra which is true.
Yeah, since in the boundary, it's not like a product of Hilbert spaces. Certainly, there's something you can do here that will mess up.
What do you mean the boundary is not a product?
Meaning, suppose you had a product of Hilbert spaces and your U acts on one product, U prime acts on the other, then you're safe. Right?
Yeah.
But that's not the structure of the boundary.
Why is it not structured? Are you going type C on us?
I was thinking.
The boundary is like two causally disconnected. Right?
No, but I was thinking this business about Harlow that if you take a bulk operation outside your region, there is a way of having it supported on the boundary that includes your region.
A bulk operator. Yeah.
Okay, so that cannot exactly commute with everything on this region. So it's not exactly some product structure. No, sorry.
The boundary is a product structure.
Product also.
Boundaries are products.
Remove double, you can consider remove double, for example. I mean, just this CFT and that CFT, everything.
Yeah,
is totally disconnected.
No, but we're talking about the part on the bulk. Suppose I have this is my region. You're trying to define an arithmetic axis.
Yeah.
Now, suppose I define this operator. It can be supported like this, right?
Yeah.
So it can't be like this part is one product and this part is another. This bulk region is one product and this bulk region is another.
The bulk region is not a product, that's right. But
that is the kind of thing you're trying to do, right?
No,
U primes are
I am not
outside bulk.
But I am just using commutativity. I am not using anything else.
Right. So you're using
And within the code subspace, capital U and little U can be commuted. Within the code subspace, boundary commutators restrict bulk locality.
Within the code subspace. But it isn't like there is a field theory Hilbert space structure where U acts
Little U and little U prime do not act
on a different product.
I'm not even assuming that.
Yeah.
I'm not even.
And that's not possible, right? It's not.
Yeah,
It's not possible. But since that's not possible, then I would imagine there's something you can do on the U prime side that will muck this up.
If you include non-perturbative connections, yes. So if you have two bulk operators which are space-like separated, including dressing is also space-like separated, then the commutator is exponentially small in general, not zero.
You must go you just to ask and you all can explain. My understanding is that the boundary theory has a product structure.
The boundary theory is a product.
But the bulk code subspace states are built out of the boundary states in such a way that they can be reconstructed partly on one side or the other, right? I mean,
Right.
Yeah, within the code subspace.
No, but the question I was asking was this. He's now looking at two bulk regions, right? A bulk region R and a bulk region R, right? Okay, and he wants that no matter what you do on the R prime region in the bulk, it doesn't affect your action on R.
Up to exponentially small directions.
Okay, so that's what I was saying. Yeah.
Okay, the
There's
output-
no exact structure in the boundary that respects it.
Yeah.
No, but even from bulk point of view, what is that?
Huh?
How can you do such a thing where you change this side and not this side?
Well,
That
if
was
it was a quantum field theory, it would be fine. Right?
Yeah, and
The bulk of
you just make sure your dressing doesn't
It's
go.
not, I mean.
It's not. I know.
No,
That's-
I'm saying your
I know.
make sure your dressing doesn't cross here. Then it's exponentially for small computers.
Ronak, let me ask you a very JT specific question because that's where you do the calculation. Are you saying, okay, the usual calculation many times done is that you take G Newton to go to zero, which you can phrase in terms of the dilaton, number of scalar fields to go to infinity, keeping the product
That's-
fixed and include back reaction.
That's exactly the limit I will take.
Okay, because in that limit, consistently, you neglect all, higher order in 1 over G Newton even, not only e to the minus 1, but
Yeah.
even the powers, because you solve classical equations with matter quantum stress tests, right? So if that's the limit, there's a rigorous limit
Yeah.
one can justify.
I think that is true. I am never.
But you could even go beyond by including perturbative in G Newton, but not e to the minus 1, but you might not even be going that far. And I don't know what
I am not. I will take only perturbative CG Newton.
Okay. But this is an aside, but when
This is-
people, for example, did all the
GS,
generalized second law, this, that, and the other, they work in a particular limit, they don't really solve quantum gravity of JT with matter exactly, that's too much, right? So they work in the following limit where matter is treated quantum mechanically and the classical GR equations are solved. And that can be justified by taking a limit because you have n scalar fields or something. Take n to go to infinity to amplify the quantum effect of matter. Take Gn to go to zero to keep the gravitational part classical. So I was just asking whether that's the case. If that's the case, then there's a rigorous way to.
Okay, I'm sure there is. In this, I am very physicist, and I don't think about what the rigorous way to do it.
Okay,
But I think you're right.
Because you have JT, you have so much freedom.
Are we in a JT context here? Or
Yeah,
what?
he said.
Okay, the main
At
topic.
some point he said it, so that's why.
Okay.
I want to apply it in future to higher dimensions also, and I'm working on that. But today is cheat.
Oh, so then my question probably makes no sense. Because now there's only one bound.
There's no point.
But
This is the same issue. The same issues are there. What is it is entirely relevant. Okay.
Okay, you can take outside and put some things.
On the left, on the right. Yes. It will in general.
So then in the order of big Q and small equal and the IT order, because you said it only coming to
This means up to exponentially small conditions, and that is fine.
the exponential the
Small the point is that your coordinates will not be spoiled within WEB side. It will only be for quite a form. So yeah, it's fine. Okay, so now let me translate this into a consistency condition and entanglement wedges. And again, entanglement wedge is not the region bounded by the QES. I'm just bad at naming things. Okay, so the first consistency condition, which was introduced in 11 years ago now. Maybe even more. Okay. A long time ago, it's called causal wedge inclusion, which we already discussed, which is that the causal wedge of B should be inside the max CW of B, and the causal wedge of B bar should be space-like separated to the max CW of B. Okay, that's what these fancy equations of are saying. Okay, so this is called causal wedge inclusion. What I will extend this to something called complementary causal wedge exclusion. Okay, and it says that basically actually any unitary EFT unitary on WEB bar. Okay, remember I can't take the bar inside the brackets here in general. But the space-like complement of this guy act with a unitary here, and it should not be possible to move the causal wedge of B bar outside the column. Okay, this is complementary causal wedge inclusion. Okay, and
Let me just make sure. So you have WEB, then there is the region which is space-like separated from WEB, which we are calling WEB.
full bar, yes.
And then the statement is that you Say this.
For any EFT unitary on on this side, okay, you can't, the back reaction will change the relative location of this point and the boundary B bar, but it can never change it so much that they become causally related. They always take space like separate.
So Ronak, one type of view that I can think of you prime which will do this kind of thing, you just the move time shift on the right side, right? But that's something crazy in the bulk, right? If you just move things in the right side.
Yeah. I will very
So
important.
how do we kind of know that there are such unitaries?
There's something called concourse cycle. It does exactly that, but it does not do precision.
Okay. Oh, I see. That.
Wait, was your condition that you cannot act with a unitary of any sort, no matter how complicated, on B, and then affect something in B bar?
Sorry.
So with acting with a unitary on B, you could affect something all the way into this gray region, right?
Yeah.
Unitaries are.
But my definition is the definition of subregion duality uses this U prime. Right?
We're saying no.
And I'm just saying that.
Prime you use, this guy should always be spaceless.
Yeah,
That's the
because
same thing.
see, if suppose I was able to bring this up here, okay, then there would be an operator, local unit, simple operator here, which should be in capital B, but won't commute with capital B, and that violates boundary causality. Okay, so
Instead of keeping back reaction up to all orders and all orders in perturbation theory, but neglecting e to the minus.
yeah, I'm neglecting
Right, so that means like when the corrections are of the order of e to the minus e to the minus 1 we can you have the wrong answers and that.
Like, see, if you have two in the bulk, if you have two space-like separated things, the commutator is not zero in general. It's just exponentially small. Okay, the bulk locality and bulk causality, microcausality are just not preserved at exponential level, and that is just a fact about gravity as we know it.
So would that also need some fixed?
Yeah, but that's what all those squiggly lines were. The squiggly lines were exponentially small directions.
Your last condition was a condition on what?
On like given if for the bulk dual of capital B, this must be true.
The bulk dual, I say, for this entanglement, right? I say.
Yeah.
Okay.
Yeah. So this is the thing, and so this is just the dressing story that
And B and B are bar are the two ends of the two boundaries.
yes, capital B and capital B are the two boundaries, and yeah. Okay, so now let me just tell you about the theory I will use. Huh? More questions? Okay, so I will now restrict to JT gravity. Till now, nothing I said should be specific to JT gravity. So I should have the further limits Sandeep mentioned is important. Okay. So the action of JT gravity is some topological term plus the dilaton times R plus 2 plus a boundary term plus the action of a CFT, okay, which couples only to the metric. And it's given by a boundary there's a boundary condition that phi on the boundary has to have a particular value. This phi r is like 1 over g Newton, it controls perturbative corrections. Okay. And this S naught controls non-perturbative corrections. It's a funny theory with 2 g Newtons. Okay. So the dilaton is like the size of some internal space. And the CFT, as I mentioned, couples only to metric. Then I will, as Sandeep mentioned, take this order of limits where G Newton is much less than C G Newton is much less than 1. And I guess the correct statement is that I'm being non-perturbative in C G Newton, but taking G Newton to 0. Is that the formal statement?
Usually that's what.
Okay, good. So I have not thought about the formal word, but yeah, that sounds right. Yeah. So the point here is that I will basically take the curvature is going to be -2, the metric is completely fixed. And what's going to happen is that the dilaton is dynamical, and because of the boundary condition, the boundaries will be dynamical. Okay. And this order of limits for me allows me to take the dilaton to be a classical field.
I'm sorry, and from the point of view of horizon care of black holes, you can do this because one mode becomes very very much more strongly coupled with everything else.
Yeah, basically.
So you can take that coupling to be non-zero, but set everything else.
Yeah.
Hmm.
This is okay. This is something I remember from, I don't know, 7 years ago. Yeah, but yes. Okay, good.
So here the B is left in this context. B is just left in B bar is right?
Yeah, it's going to be that, yeah.
So why do you draw this green wedge small?
It's
It should be the full thing.
no, because what happens is the boundary particle, like if this is in some coordinates where, this thing has infinite length. Okay, so the induced metric is like the time is used as a time coordinate, the boundary time coordinate. But like in some particular metric, which is this one, it can look like this.
No, what I mean is that if there are 2 points, right? Boundary 2 points always.
Yeah, boundary 2 points, which is 2
So
lines here.
this is B, then this is B bar, right?
Right.
And then this full thing is this causal wedge,
No.
which would no?
No,
If it is just a
actually,
point.
because the point is that I will work at finite epsilon and take epsilon to 0 behind, and what basically happens is that the boundary, which is defined by this, kind of looks like this.
No, but it doesn't matter how it will look in the bulk. As a boundary, it's just 1 point.
No,
So it
this is a weird gauge. There's a weird choice of coordinates where the location of the boundary is dynamic. Okay.
Oh, that's your boundary. That small triangle is the boundary.
These green lines are the boundaries.
And on that side?
The
Oh, just
green
that.
lines.
Okay.
Yeah.
Fine.
Yeah. So the part that
And what is that dotted line then?
good.
Just
This
some-
dotted line is just it's a coordinate when w equals 1. Okay, and like there's no real. The point is it gets weird because there's no singularity in this, so it looks funny. But yeah.
The boundary then coordinate, sorry,
Yeah.
that coordinate, this wedge doesn't reach that dot.
Right now it doesn't because there's some. This is I was going to get there. So in the thermophile double, they will both wedges will hit the dot. But if I add some energy on the right side, then basically the right boundary shrinks in these coordinates.
Oh.
It's not really shrinking. It's not a true. It's a coordinate.
No, but then it should. Is the fact that it is not reaching that dot is not a coordinate arc.
Yeah, that is not a coordinate. So the shrinking of the boundary is coordinate.
That's-
These are called. Yeah. So this is like happens in the ADS value. This is an ADS value.
Saying, the reason why, I mean, it's not certain. Why you get black holes is that, the boundary moves after a point at the speed of light. So you have a horizon because
Yeah.
we all think that line.
Yes, that's right. That's completely right.
It's a bit misleading to think of it as timeline going on forever.
Yeah.
So I was more like trying to get at this wedge not reaching that.
Yeah. So
dot there.
typically energy in the bulk will make the wedges not sweet.
Okay.
That's the important point I was trying to make with that. So that brown line is like a shock.
And the shape of this boundary is determined by some matter inside, or it's just a choice?
Yeah, basically because what happens is that there is a. Did I write this down? Okay, I forgot to write the equation. The equation of motion couples the dilaton to the stress tensor of the matter, and the boundary is given by this boundary condition.
So the matter was forcing this.
Yeah, the matter
So
for
it's not a choice of what you're doing.
Yeah. Yeah.
No.
Yeah, it's exactly it's Coulombic back reaction.
So just, ADS2, pure ADS2, you can take global ADS2, which goes on forever.
Yeah.
Then you can choose a set of coordinates, which gives you the ADS2 black hole.
Yeah.
And there's nothing, it's just a choice.
Yeah.
It's the same space-time, but you can view it as a black hole or as a zero temperature. It's not like that.
No, it's not like that.
Yeah.
In fact, I will do everything in global ADS2 coordinates. Okay. Well, like, yeah. The point is that these boundary particles, as they're called, determine the actual location, the causal relation.
Yeah, so in fact, this is that ADS2.
Yeah, this is the global ADS2 coordinate.
And here, what's different is that there is one additional element, which is where is this boundary?
Yeah, exactly.
Are you going to import any energy?
Connect. Okay. Good.
Or the average.
I need QNEC, I think. But QNEC is true here, so it's
Classically, you're in no quantum back.
no quantum aggregation.
No quantum.
Yeah, good. Because I am in this limit, which makes sure that the dilaton, which is the gravitational part, is
Does it not matter?
Matter is arbitrarily quantum.
No, but then the matter stress tensor will violate.
QNEC.
QNEC, he said QNEC.
QNEC is including quantum corrections.
Sorry, I get confused.
Oh, actually, I will need not QNEC. I need something weaker than QNEC, is called the QANEC. I will get to QANEC later.
I mean, the QNEC is not, is, the matter back reaction satisfies Q, is,
It's expected to be true of general,
Yeah.
boundary cover.
I mean, it certainly satisfies ANEC, but.
No, I will use something.
I need to know what QNEC is.
I will use something called QANEC, which is slightly weaker than QNEC, but yes, it's stronger than ANEC.
That's like the integral
A half integral.
of.
Yeah.
I thought that was ANEC.
No, the Q is important because I use the quantum term as well. Good. Okay, so the point which is that I will fix coordinates with W and W bar. W, kind of funnily, W bar goes up into the past. Okay, this makes this allows me to get rid of many signs. I like these coordinates better than the one that go. Okay, and a small bar means complex conjugation. Big bar, complementary regions is big bar. See big bars. This is a tiny one. Okay. Good. Everything I do, there are like incommensurable parts with everything. Okay. Okay. So now I go to the coordinates, but there's a residual SL2C symmetry in this coordinate, which we can use to take any point P in the bulk and give it to coordinate location 0. Okay, which I will do later. And yeah, the reason and 0 is nice because certain Richthofen symbols vanish on the light one of 0, but not on 0. Okay. The other thing is that it looks like the boundary is like curved or whatever, and the matter might care about this, but actually in the correct order of the matter doesn't care about the fact that the boundary is curved. Okay.
So if sigma if W is tau plus sigma and W bar is tau minus sigma, and sigma runs from 0 to pi or something, this from boundary to boundary. Okay. So it's like a strip for the string, right?
Yeah.
Okay. And that's just a Y factor. Which,
Yeah, exactly.
Okay.
These two boundaries are W bar equal to 1. So
yeah.
Okay. Cool. So that is the gauge. So now I'll take 2D CFT, and as was just mentioned, this metric is just a flat factor. So for most purposes, you can forget the CFT doesn't even realize that it's an ADS2, it's not a okay. And now
but there are boundary conditions at the end of the open string.
it's some cardinal string. Good. So now if the point is that I am working in these coordinates, but this is not exactly these coordinates because W bar equals 1 is the coordinate location of a hyperbola and right to right. So this is what happens when I actually draw W bar coordinates. And now this manifold has a boot symmetry.
Sorry, my sigma equals 0 would have been straight up.
Yeah.
So okay, fine.
Yeah, but there's some tan or something.
It's because it's not the boundary is not really the boundary.
No, it's not that. It's not. It's that this I'm going to work in epsilon going to 0, where this boundary particle is effectively going. It's just a conformal frame, really.
Okay.
But the point is just that I'm drawing this in tau sigma coordinates, right? But now I'm drawing this in W bar coordinates, where the same boundary which was straight in the previous slide. Now I have here.
Nice.
Okay. So yeah, I was just kind of lying to you in the previous slide. Okay. But the point is that this surface, despite what you might guess from here, ADS2 has a boot symmetry. Okay. And it basically just looks like this.
But why are we using ADS2? This is not valid for general states.
No, it is not because the bulk CFT does not know that the boundary particles are in.
Boundary particles. No, I thought this state, any other state. The state that you have here with a matter where you have this separated.
No, the manifold.
Separate.
The manifold always has the boot symmetry. Okay.
Even with this matter.
Even with this matter, because these boundary particles are not really going out of the boundary. Okay, this is just a way to visualize the conformal frame in which you are approaching the boundary. Okay, and so the manifold, which never changes, always has a boot symmetry. Okay, but there is a particular state of the CFT which is variant under the boot symmetry. This is not that state.
So your analysis is not applicable to that state?
No, I didn't say that. I'm just saying that I'm making a statement. I'm not saying what I'm not saying.
Okay.
Right? I'm just saying that the manifold always has a Boost symmetry. There is a state which is invariant into that Boost symmetry.
Okay.
Other states are not, and that is fine. That's crucial for whatever.
And the state here is just the shape of the Wheatley boundary. Yeah?
The state of the gravitation, the state of the gravitational part of the shape, but there's also Q of T
Sure.
state on the slice.
Sure. So that would be the unique SL2R embedded back in that kind of thing.
Yeah, omega is the center invariant vacuum.
Yeah.
And you know it's a bulk state because it's a small omega.
Yeah.
Okay. Good. And so now we know because of the Boost symmetry,
Yes.
the residual density matrix of this omega generates this boost on only the right side. Okay. But because it's generating the boost only on the right side, it does something crazy here. Will create infinite amount of energy at the horizon. So it is not a good option, just a bad option. Okay. But there is a good unitary which basically does something very similar. So given two states, given omega and like psi, which will be the actual state we are interested in. Okay, you can define as US prime, which is some combination of the density matrices. Okay, which for an operator in the right wedge, so for an operator in little b prime, will basically just boost like the correlation, the expectation value of the operator will get boosted. Okay, so here this is how things boost at coordinate level, and this is the boost weight. Okay, so in the new state, the correlation function in the new state is the correlation function in the old state with the okay, that is the action of this 1 cycle.
So just so that I see where you're going, you're going to ask if I wiggle the boundary on the left, what is the new?
That's not probability.
No. Okay.
That's yeah.
Ron, just so I understand, the left and right wedges are defined vis-a-vis the two boundary asymptotes.
Right now, no. So good. There is a. I'll take this moment to make a. So whenever I call a wedge WE B psi, okay, that is defined as the bulk dual of capital B. But if I just say little b and little b bar, I am just defining two wedges. Okay. Little b and little b bar are not a priori related to the boundary regions, boundary particles in any way. Okay. Just because right now I'm talking about a CFT, I don't care about what the electron is. Okay, so for any two wedges,
What is some CST in a fixed background, say
it looks like this.
and then of course you can do it. Okay.
Yeah.
So CFT, when you say CFT, it's a bulk C.
The pulse. Two, yeah, exactly. Small letters. Small letters.
There's little size, but the excited state.
Yeah, will be some state which will be actually be integrated. Yes.
But ultimately, because of back reaction, the geometry will change.
And I will put a step by step. Yeah. But right now I'm just saying this is the EFT operator, which you conjugate an operator by the EFT of like you take O, you conjugate it by US prime, it's converse cycle flow. It looks like just boosting O in the original state. Okay, and it is a well-defined unitary in algebraic QFT, as you can see from this. Okay.
You might use the fact that back reaction changes the structure of time.
What do you mean?
Means the fact that they may become type 2.
Oh, that is not something. In fact, this is going beyond that because I'm giving CG Newton finite. In type 2 story, CG Newton also given. So that yeah. This is not directly comparable with the type 2.
So what is your about?
It's just the CFT algebra, which will eventually address.
So you're not taking dressing.
Right now, I'm not, because this is about 2D.
So it's type 3.
Yeah, right now it's type 3, but I am saying that even after dressing, it's not like it's type 2, because this is not in the realm of applicability of that. Because that story is one where back reaction can never compete with the original, with one. Whereas here it can. It's crucial. Like, yeah. One of the motivations was like my annoyance is that everyone was so excited about like things without back reaction.
Ronak, what was wrong with density matrix?
It's just a bad operator. Like it, what it does is it boosts B bar without keeping B constant. So it creates a kink at this horizon here. Okay, and that kink is really it basically leads to a infinite amount of stress tensor at the horizon. Okay, the energy is infinite.
So it's a bad operator from the point of view of the bulk. On the boundary point of view, it's an okay operator.
If I put a capital letters here, yes, but these are small letters.
So it's a crazy operator. It does something crazy to the bulk.
No, yeah, and like it's not it cannot be mapped into the boundary. Okay, there is a different operator rho capital omega capital B bar, which is a fine operator, but it is not this.
Okay.
The Brits bulk goal is not this.
The kink is not happening in this one per cycle.
Yeah, con co-cycle, what it does is it basically like it kind of tries to do a boost, but then it undoes the boost to it undoes something else. Okay, and what this does is it takes the UV modes which are getting kinked over here and unkinks them. Okay, but only like boosts the IR stuff. So like only operators expectation values get boosted.
Uses that omega and psi is the same on the left.
No, it does not use that omega and psi are the same on the left. It only uses that they're in the same Hilbert space. So like the UV structure is same. Yeah. In fact, when you write it out in terms of deltas, it will be one of these will be a normal delta and one of them will be a relative delta, so that whatever on the left cancels it. What is the question?
Just what are you? I was asking what you're going to try to show.
I'm going to try to show that unless little b, I'm going to try and violate this condition.
Okay.
Yeah, and basically this boosting property of the CC flow is going to kind of push this stuff up. Okay, so this is my review of today's CFT. Okay. If you didn't understand what the CC flow was, don't worry. I will like give you pictures. Okay. So let's consider just the thermophile double, which bulk matter beams are in Harlow state. And the point is that, and this is the Cassini-Verta-Myers argument that the entanglement wedge of B in the thermophile double is fixed entirely by causal wedge. Okay, because we know that the entanglement wedge has to include the causal wedge, which means the boundary of the entanglement wedge has to be space-like to both boundaries. But there's literally a single point that has satisfies that property, right? So, yeah. So that means that this is the only CWI completely fixes the max CW in the TFT. Okay. And earlier you guys were discussing whether Cassini-Verta-Myers is a Euclidean. It doesn't because of the radius. That's not the word they use, but it actually is. Okay. So good. And here, by the way, I've drawn these lines. I'm just drawing these lines to make you think about in which direction the electron is increasing. So out here, the electron is increasing to the past. Out here, it is increasing to the right.
And Ronak, you're trying to show that you cannot violate, or you use the fact that you cannot violate your condition as you change what? As you change the bulk state in the field theory?
Yeah, by acting with the diagram. Yeah, including the backreaction of the
Changing the bulk state and then including backreaction.
Yeah. There's a paper about like doing it step by step. We had some arguments in a paper with Adam Levine and Arvind Sharbazi Mogadam in 2020. But today I won't deal with that certainty. So yes, I'm changing the bulk state and then taking back. Okay. In the paper, I actually explained why I don't need to worry about that certainty. But today I won't. Okay. So now here you can see that like things are increasing. And one other way to think about the fact that every point is connected to the boundary is that if I go along the null ray where the delta is increasing, the delta keeps increasing. It never goes down. It never does not like settle, right? So the basic idea is, whereas if I go here, the dilaton is literally the same as I go this way. Okay, and if I go here, if I go like up, the dilaton keeps decreasing to minus. Okay. So one way of thinking about whether a null ray hits the boundary, okay, in a way that's completely local to a null ray, is to follow the dileton and see if it ever stops increasing. If it never stops increasing, you're hitting the boundary. If it decreases, you're hitting a singularity. And if it's like it goes to a constant, you're hitting the top of the constant. Yeah, top of the constant. So this is what this slide says. Given two null rays, so theta is called the expansion, which is the null derivative of the dileton. Okay, and I will use theta at given null rate at w bar equal to w naught bar. Okay, which means it's right moving. Theta at infinity comma w naught bar will be my diagnostic of whether I'm hitting the boundary. Okay. So and yeah, so if I hit the boundary, theta is greater than 0. If I hit the singularity, it's less than 0. Yeah. And in particular, if I set w the original point to 0, 0, which my residual gives me tail of Puchito. Okay. The gravitational constraint on the null surface is this. That the null derivative of theta is the null component of the straight. Okay. Which means that the expansion at infinity is the expansion at the original point minus the half average nullity. It's half because this is not minus infinity but 0. Okay. So this is called the Hani. Half average nullity. Good. Okay. Let me go back to TFT. What's happening now in the TFT, the right hand side here is 0. Okay, the bulk state is little omega. Okay, both right? Which means that if I go here and theta equals 0, I keep going back and theta will always be 0 because there's nothing to source a change in theta. Okay, and so this point is the one where theta equals 0 in every direction. The dileton is invariant under every wiggle, which is what it means, which is the meaning of extremality. And basically, what I'm going to do is I'm going to try to create an empty horizon like this, so that the expansion at late times is the same as expansion at the original phase. Okay. Okay. So I'm going to try and get rid of whatever was the right answer. Okay. So now again, let me just do the quantum boost. So again, we are back to CFT, not yet, but so take a bulk region, which is a right wedge, W greater than 0, W bar greater than 0. Its boundary is 0, 0. Okay, so the result I just do. And I define the quantum expansion of the boundary to be the classical expansion of the boundary plus the null derivative of the entanglement entropy of little b. Okay. Now, because I'm talking about entanglement entropy, I have to talk about regions as number of points. Okay. And now I take this equation, I add and subtract derivatives of entanglement. I get that the expansion at late times, in the future, is equal to the quantum expansion at the original point minus what's called the quantum half-rate energy or the coarse-grained. Okay. This is called the one. Okay. And this guy is always a positive. In QFT, is a positive operator. Its expectation value is positive. The reason is that it can be related to monotonicity of relative entropy. Okay. So to calculate, if I give you a bulk region little b bar.
Let me just make sure I understand. So you add to the area or the dileton rather, you add the entanglement entropy.
Yeah.
And then you define the expansion.
Yeah.
Which is just a derivative along the null direction, right? Okay, got it. So that's theta.
Yeah.
And then what did you do? You follow whether theta is increasing or not.
Yeah, basically. I'm interested in like
you okay, sorry, yes, please. You compute what is the zero?
Okay, so-
Sorry, just that.
So point is I'm starting from 0,
You
and I'm calling a null
start-
rate.
Okay,
So
so
W will increase, but W bar will
fine, fine. Okay, so it's the other coordinate. You follow it all the way to infinity, and it is the value at 0 minus the not just the stress tensor, but this additional code.
Yes. Okay, it's called the Quani. Okay, this Quani, the positivity of Quani was the thing that turned out to be GSL in Adam's rate.
Say the positive.
Positivity of this Quani
Yes.
is equivalent to the turned out to be the generalized second law.
In QMT that requires a regular.
To define it like this, but you can just define it as a derivative or relative. So the it's perfectly.
But this.
This expression requires derivation. Yeah. But
And this theta was along, was
null rate.
a null rate, any null rate?
Here I'm taking it to be a right future null rate. But like you could most of these equations with some appropriate signs work for any number.
But it's not some event horizon of a black hole.
Right now it's not. No, this is just right of the equation.
Okay. And do you have some expectation of what happens at infinity? That along an event horizon of a black hole, you expect this to settle down?
Yeah, so that will be 0 in the event horizon.
Yes, but here on this, even at infinity, it could be non-zero.
Yeah, exactly. So
Okay.
I will use the value of this guy on the right hand side to figure out whether it's an event horizon or not.
Right.
Okay. Is there something?
It's just confusing. Sorry, just to state it. We just the way the generalized second laws work for black holes in this theory is that okay, you have the classical law where you keep classical matter and just the dilettron. And then you have the quantum version where you keep the quantum back reacted stress tensor and the entanglement plus the dilettron, right?
Right now, there's not the generalized second law.
It's not, but here you're keeping the quantum stress tensor in T plus the additional quantum.
This is the entanglement entropy part.
Yeah, but that shouldn't enter in the. This is the area. Okay, yes.
So like this is
Okay.
the generalized second law comes down to the fact that the generalized second law comes to the fact that this quantum expansion focuses. Okay.
Yeah.
And yeah. So that's
Yeah. Okay, so I think I'm just confused. about some-
the difference is that there you take this left hand side to be 0 because you care about event
Yes.
and then you use the positivity of this Quani to point out that this guy is always positive.
Right.
Okay, and that's the generalized second.
Maybe you are in a better situation because you're in 2 dimensions.
Much better situation.
Because in
Significantly
that situation,
better.
you don't have to worry about that.
Yes, significantly better situation. It's not very funny.
Yes.
Yes.
And
So the classical analog of this would have been theta would have been the entropy, and EQHA would have been just stress tensor.
yeah, this would have been classical expansions, and I just don't have this,
And you would have used null energy condition
yeah, exactly.
classically.
So, not taking the higher derivative things.
I'll call fx by theory.
Sorry?
I fix my theory to be JT plus CFT, so it doesn't have higher derivative corrections. One could study higher derivative corrections also, but I just have none. Yes. Cool. Okay. So the point is that we will use this right hand side we will calculate the right hand side for a given point and like it's null rate to figure out whether causal value inclusion holds. If I find out that the right hand side is positive, that means that I'm in the causal. I'm like if I find out that if I take a point to the partial causal width, okay, I will find that the right hand side is positive because I'm hitting this and the expansion here is positive. Okay, so I will demand that the right hand side be non-positive. That will be causal value inclusion. Okay, and CCWE, which is my new thing, is just causal value inclusion in different geometries. Okay, so now let's see.
Double state or
No, this is just a fact about 2D shape. Like everything I've told you here is just right of the equation, which is just true in any shape. In particular, psi is not the homophobic.
So even this I did close. So this is so suppose I took in ADS5, I took an internal black hole. I look at the expansion of the GD6 on the horizon, of course, it's 0.
Mhm.
You're saying now if I take like a little Poincare patch that's inside of the black hole on the right, then that expansion near infinity would not be 0, but would be
Infinite.
infinite and infinitely positive.
Or positive, because like you can see that like any surface is just kind of doing.
It's becoming big. It's
Yeah,
like,
that's basically
yeah.
it.
That's the meaning of the horizon, right? There is
Yeah.
boundary trapped surfaces, right? I mean,
Yeah.
there is, you take these, what do they call those bouquets or whatever, they expand out.
and this one
Yeah,
just is
light sheet?
Yeah.
Oh,
Are you talking about light sheet?
Actually, but there's some word, no, anyway.
And then towards the singularity, it shrinks. It
Yeah.
shrinks.
Yeah.
And then the boundary.
Yeah. So this is like, for example, the precisification of obvious things that was used by Penrose to prove singularity theorems.
I see. So some of these pointers, if you take like a torch and you shine it, the light rays go outside and focus in.
Yeah.
I see. And this. Fine.
Yeah, exactly. This is what's happening. Okay, cool. So now let me just so consider a state, okay, which little psi in the bulk. Okay, I am not again caring about what happens on the boundary yet, or what happens to the electron yet. So, and as a toy, the state has some energy going towards through the future horizon. Okay, this is some. So now let us see flow this. What happens? The first thing that happens is that this energy kind of gets boosted off. And the stress tensor is a weight 2 object. So it gets boosted off and smaller. Smaller? I don't know, like it becomes smaller. It gets an e to the minus 2. Okay. Then a couple of other things happen. At the boundary, okay, I get 2 more null shocks. Okay. And the amount, the strength of the null shocks depends on the derivative of the entanglement. Okay. In particular, for S positive, and if the derivative is positive, this is a negative energy shock. Okay. And as you take S to infinity, this guy violates what, this guy saturates what's known as the quantum knowledge condition. The shock here. It's on the negative energy null shock. Okay. And so this is a really cool thing about the CC plan. This is why I kind of love it. It's like it literally converts entanglement into energy. And this is the sort of thing you need to think about the interplay between entanglement and the emergence of space-time and so on.
Sorry, just in very concrete terms in this model, you're injecting two shock. Is that what you're doing?
I'm acting with this, I'm looking at a different state where I acted with this US prime.
But the different state is the original with two shock waves along the two.
Two shock waves and now all energy on the future horizon is boosted off.
Boosted?
Boosted away. So like it was here. Okay. Now it's further away. The energy flux.
By some finite amount.
Yeah.
By some shift.
Yeah. This S parameter tells you how much is being boosted. So as you send S to infinity, this kind of gets infinitely boosted away, and the exponential factor becomes infinitely important, and it then becomes 0 as S goes to infinity. Okay. What this means is that in the state with US prime, the quantity is e to the minus S times the original quantity. Okay, and as S goes to infinity, that goes to 0. Okay. So like you literally what the CC flow does is it boosts away the quantity. Okay. So this you don't need to know what a CC flow is. You just need to know that this thing quantity which tells you about the amount of quantum focusing in the theory is getting boosted off to 0.
But I mean, what I want to say is there's a state in which this is happening.
It's a good state, yeah. US prime is a unitary which is in the Hilbert space and lives only in B dot. Okay. At the AQFT level. There is the US prime size is a good state in the Hilbert space.
But on the, I mean, isn't it some kind of fairly extreme violence on the gravitational side? I mean, you had some some nice stress tensor, and now you've just taken the
push it all the way.
So it's a finite shock. Okay, so it's like ADS Pegas or something. But of course, when you try to construct US prime taking into account back reaction, it will spread a bit because US prime is a product of things. and like we'll have some right? So these shocks will get spread out. So it won't be that violent. But anyway, it's a finite shock. It's
And just going on along some things, let's say you started with some state, now you act with this unitary whose effect is to create one shock here and one shock way into the future. Sorry.
No. Well, if you so this is this so you have your original null horizon. The original null thing had some structural flux through it.
From the state.
Yeah, in the state, original
Yes.
state. And whatever flux was there gets boosted.
And what is that first line that you're drawing?
This one?
Yeah.
So now there are two shocks basically.
Why was that set? Why was that set? So I thought you were just taking everything and pushing it all along.
So that's what happens to the original state energy. But also there are two shocks which whose magnitude depend on entanglement derivation.
What do you mean by two shocks? What is sorry? Yeah, saying the effect of the unitary is to create these two shocks.
Yeah, in US prime psi, this is what the stress tensor looks like. Like this is T and this is T bar.
I see. So you boost plus create shocks.
Yeah.
Shock is at the boundary of P bar.
Exactly at this thing.
So it's not supported outside P bar.
It's not supported.
These shocks are shocks of the matter stress tensor.
Right now, there's no gravity.
So everything here is acting on just the matter QFT.
Yeah, there's no gravity.
So this is QFT analysis.
Yeah.
Okay.
And
feature of one.
yeah. Yeah, this is not my QFT analysis. This was done by Cyan and Poplar.
And this shock doesn't extend to the P events.
It does not extend to the wheel. Very good.
And just in practical terms, is this a state of matter? So to begin with, we have some nice overlapping state of the matter fields, let's say.
In that case, nothing will happen. Because you're using this US prime, this PC flow, uses a base state. And as the base state, I'm using the Harlow state, which is brutal.
Okay, well, if you want to do something else, okay, we have some nice wave packet.
Yeah,
something
exactly.
riding along, right?
Ah.
And now the Cone-cos cycle, can we think of it as is it a very quantum state? Is it a classical shock wave, just very focused? What is it, just physically?
Like quantum, I talk about fluctuations.
Uh-huh.
Are you asking about the amount of fluctuation?
Yeah,
I think
I'm
the
just asking.
fluctuations have not been calculated, I believe.
Can it be thought of as like a coherent state?
Yeah, is it like a coherent or is it some very squeezed
Yeah,
scale? Just to understand it.
So
physically.
if this was coherent, it stays coherent. These two shocks, I don't know that, I don't think anyone has calculated the fluctuation. That's an interesting question which I will.
Okay, but so I'll let you go on, but can it be understood as some, Bogoliubov transformed kind of state, or is it some much more complicated? Whatever, is it sort of understood, or is it?
I have
is it
calculated
mathematically
this.
you understand it?
I have done this. I have written the state in like three fermion CFT for three fermion theory for two intervals. And there the one could write in terms of some sort of Bogoliubov type transformation. But I think that's very special to that particular theory.
When you draw these shocks, how localized are the shocks?
In AQFT exactly looking.
How can that be finite energy?
It's a finite. What?
Usually, if something is zero size and position, it's infinite scale and moment. My answer.
No, because here just you can prove that you can prove very rigorously that like the delta function has a particular. Oh, it's infinite energy because it's delta function. The integral is finite.
But integral along what?
The integral along the horizon.
I see. You're saying it's an infinite energy density, but finite energy.
Yeah.
Okay.
That's it. Yeah, that's the point. Okay, but the point is that what it does is it kind of boosts away the quantity. Okay, so what it does, and remember, quantity is the thing that makes horizon null rays non-empty.
Makes null rays?
Non-empty. In terms of the when you think about the right side of the equation, it is the thing that sources focusing. Okay, and then removing all focusing using this one. Okay, so here's another way to visualize it. So suppose this will be
The SE there was the entropy of psi or the
entropy of psi in the to be.
wasn't the difference?
It is, oh yeah, it is this is delta SC, SC psi minus SC.
Oh.
Yeah, yeah, you're right, you're right. This is also delta T. I thought the delta is
Difference between original and now.
but between the omega state, between the base state. Yeah. So that's why that's why these things are finite. Otherwise, okay. Here's another visualization I have. Okay, which the referee will put in. So suppose you have, you have your. So this is a null surface, and I'm thinking of the dilaton as the size of some circle, and this is my my boundary of P bar. I don't know why there are P's everywhere. It should be P bars. And suppose it's collapsing into singularities. So theta is less than 0 as you go. Okay. After you do this thing, what can happen is, first of all, typically the you kind of defocuses at this point. Okay, because this shock might be negative energy. Okay, so you get this leg thing, and if it goes and hits the boundary after defocusing, then it will keep increasing, or it can like become a cylinder asymptotically, which means it's hitting this corner of the time. Okay, or it can continue to focus, in which case it's hitting a singularity. Okay.
What is this dotted line?
It is the boundary of it is this.
This is a higher dimensional picture.
Yeah, I'm just saying, yeah. Like this is what happens to the dilator. Okay. So now let's get to the main argument. Till now I've been setting up the pieces. Okay, so first we need to put in assumptions. And so first assumption is going to be complementary recovery. Okay, which is going to I'll tell you what you can say without complementary recovery later. But basically the statement is that the complement of the EW of B is the EW of B. Okay. So B and B bar can be treated symmetrically. The second one is going to be the CCW condition, which it's not something I've proved, it's just something I argue for plausibility.
So you got CCW.
Complementary plausibility, the thing that the other problem is separated.
So, but why? I mean, it should be true, right? Because
It's true based on my definition of reconstruction. Open the paper, I actually explain why this is an assumption. I forget it exactly. Yeah, they might. So, what is the story is, because I have been so general with my definition of reconstructible sets, there might not be a reconstructible unitary in this issue. Okay, it might be there might be something funny happening, and if there is no issue of reconstructible unitary in this region, then that would be a loophole to going from SS to U to this. And yeah, it's just an annoying thing that I'm getting there. Okay, it's not super important, but it's technically it's an assumption. The sort of non-trivial assumption is that the bulk CC flow unitary for the complement of the maxi W can be addressed so that the support is entirely space like to okay. This assumption turns out to be true a posteriori, but a priori is an assumption. Okay, and right now I will also assume that the maxi W does not contain islands, so the boundary of it is a single point. There's a section of the talk which of the paper which deals with the islands, but I will probably not get to it today. Okay, so epistemically, this and this restrict the set of cases you care about. This is like cost, and this is a technical assumption which is quite crucial. Okay, and this is the weak point.
So first and fourth point restricts your del of W to be a point.
This one restricts it to a point. This one restricts says that the space-like wedge is also a maxi W of the other guy. Okay.
But I was thinking that B and B bar, since they're symmetric, that will.
You could have like a symmetric setup of islands. Some interleaving thing. Yeah, so this is the thing that okay. Cool. It is what it is, it's fine. But I'm saying that 1 and 4 are perfectly fine assumptions because they're just restricting the set of cases. The 3 is the non-trivial assumption because it's like some thing about the physics which may or may not be true.
me ask just about three, but sorry, just a more general question. It's like just so people often use the word dress and all like very confidently. I don't always understand what it means. Like suppose I had a scalar field wave packet or some operator. You say you're going to dress it to the left or right. What exactly? It's not a gaze theory, right? So it means construct some observable which involves like saying where the wave packet is in
a relational manner.
invariant terms,
In a
right?
relational manner, yeah.
So here, what you're saying is that you have some mysterious for me unitary which is generating these two shock waves, and you state the bulk unitary transformation doing it in some way which only refers to one boundary and not.
Yeah, exactly. In particular, these shocks,
That was the form of CC flow, right?
these shocks, in my assumption, will spread only into B bar, not into B.
No, but the one that you constructed with the row, it has row B bar, right? Row B bar and the row B bar inverse.
But that is not a priori gauge invariant.
Or I was thinking, you can have these shocks which you by turning on sources, you can.
But the point is, this wedge, this wedge might be bigger than the causal wedge of the boundary, right? So then, like, no source on the boundary will like go to the edge of the wedge.
Yeah, I'm not saying it's obvious. I'm just saying, would it be enough to show that you could generate your shocks by turning on sources in some region of the boundary? That would be what it means.
That would be one example.
Okay.
Typically, I expect that not to be enough. So, like in this paper, we did it via source on the boundary, and we kind of, you could only do it when the gap between the causal and the entanglement wedges was small in some unit.
But let's say in HKLL, when you say pressed to this boundary, you mean that you're defining the bulk operator in terms of boundary operators.
Yeah, that's right.
That's in that context.
Yeah, exactly. But in general, like it could be some dressing. One thing is that I wanted to be quite robust to the form of dressing. Like dressing is something that you can be very creative with dressing, And so I wanted to say something that was quite robust to dressing. So I'm only using one bit about the dressing, which is that it does not leak into the PW of the.
In particular, I could just define your algebra dressed operators, dressed in, let's say, to B bar.
Yeah.
And then define the CC flow on that algebra.
You could, but you might get into trouble where like basically because you multiply two dressed operators. Okay, the second operator you act with might not be where you expected it to be because the action on the first operator. They have to. The gravitational spreading is something you have to worry about. Okay. So, like one example for dressing would be that you dress it to the boundary of this wedge.
Yes.
Okay. You say I'm to the right of the boundary by this much distance. But now, what if something happens and it leaks? There can be leakage due to backreaction effect, and you have to. It's quite a non-trivial thing, and here we argued for pages and pages why it should work in some particular case. But here in this paper I wanted to be quite robust to the particular result. Okay, so the argument. So suppose someone hands you a wedge little bit
Sorry, the 4th point where you said the no island, that means there's only one point which is
on the boundary of the wedge here. Yeah. For the island I need a slightly stronger version of CC, which is also what I need in hydrogens. Okay. So now let's do the argument. So someone hands you a wedge little b and region capital B and a region capital bar, B bar gives you the guarantees in the previous slide. Okay. So now it's not suppose it's not extremal. Okay. Suppose rho slash B is not an extremal surface. Then there is one direction in which which is quantum expanding.
Extremal means this theta doesn't
Capital theta is non-zero in one direction. Yeah, so good. Sorry, extremality exactly means that capital theta is 0 and capital theta bar is also 0. Okay, that's quantum extremality. So because it's not extremal, that means that it's greater than 0 in some direction. Okay, so it's like if it's decreasing this way, it's increasing that, right? So I'll just by symmetry you can everything is symmetric. So I'll just take the case where it's increasing in this particular direction in positive W. Okay. Now, what do you say? So now again, you have theta naught at here, and you have the asymptotic the expansion at infinity, which is given by this one combination. And now I will act with the CC flow here. Okay. And basically because I boosted over the QH, the Kwani, after the CC flow, the expansion at infinity is going to be positive because it started off positive, and I'm removing the source that focuses the focuses the surface. So if it stays positive, that means it's sitting deep. Okay, sitting in asymptotic boundary. Okay. And here the technical way to do it is that you kind of think of a different wedge where US prime has been acted on. Okay, and then you paste that wedge on via the codimension 2 junction conditions. Okay, which basically tell you that the obvious thing is the thing that works. So if it's not extremal, the CCW is violated in one of the 4 directions. Okay, and therefore it is little b is not a good candidate for the bulk 2. It can be negative, in which case you don't run this argument, you run this argument in the opposite direction. If it's positive like this, if it's negative like this, it's positive like this. So you run it on this horizon. You run it on the horizon where it's positive. But the only way is negative. Well, that would be discontinuous. That would be highly discontinuous. Yeah. I think I assume some generosity where it's not like very discontinuous. Yeah. I am sure I put in some words to deal with the possibility of discontinuous.
Maybe I don't understand this theta good enough to see what.
No, it just this theta is like an extrinsic curvature. And like extrinsic curvature should be continuous.
Yeah.
Okay. Yeah. It's extrinsic curvature on the null surface.
If this violates CCW, rather I thought this violates your idea that you've acted with U prime and now the region B has come into causal contact.
Yeah, exactly. That is
was-
CCW. That is what I call CCW.
Oh, that's what after acting with non-trivial use, U primes and all, you should still.
Yeah.
That's what you.
Yeah,
Okay,
exactly.
And it was important that U prime acts only on one side.
It's very important that acts on one side. Otherwise, otherwise there's no violation of boundary control.
But Ronak, you can take that point to be a little to the left. Actually, yeah. Let's say that point is a little to the left. There also, I cannot quite violate this CCW, right?
If it's greater, depends on how much greater the zero is.
No. If it is here and it's not violating, then if this point were here, then
That's
it's not.
if it's not violating, that's you're fine.
Yeah, but then this is not extreme.
Yeah, but then the point is that
So even
one of the 4 directions it will violate.
that's what I'm saying. I don't see how it can violate if it is inside that. No, it cannot violate, right?
I don't understand this. If it's violating here,
If it is
Like
not
it-
violating there, let's say that point that is extremal,
then it
Right.
won't. Then the point is okay, good. So the
then
point is
that
that
will also not
if
violate.
someone gave you B which was like to the left of an extended
Yes.
surface,
Yes.
then the point is that you would use the CC flow for the complement of that. Okay, and then it would violate. Okay. So there is a very subtle thing here that but it would violate the other way actually. Here I'm using complementary recovery in an important. Okay, that like if it's not extremal, this guy is positive in one of the 4 directions. It might not violate in the same direction, violate in the opposite direction.
Yeah, but here we wanted to prove a statement about homology, right? You will end up making a statement about p bar. That
I'm using complementary recovery, no?
okay.
Yeah, I'm using the fact that the bar is complementary. Yeah, you're right, of course, it's the weakness of the argument, but it is
Okay.
this argument works very well.
Since the fact that since the statement that your on-cycle operator, which was defined without gravitational aspects, can be dressed to one side is so important for this proof. Just let me ask, the on-cycle operator, whatever is understood in the boundary theory.
Yeah, pretty well.
For JT, but say take a CFT.
There was a paper here which gave a bilateral of 60.
So then not for JT, but is the hope that in some one higher dimension case like that, you define the operator anyway on the boundary properly.
So in higher dimensions, currently I have a proof sketch only for classical extremality, not quantum extremality, for which I only need to push stuff on the horizon. Yeah, quantum extremality requires some homology to a sphere because that's where this story works. Which I don't have beyond yeah. But currently higher dimensions is a proof sketch. It's not a proof.
So, yeah, just I'm giving a summary of your argument as I understand it, if you don't mind. You're saying theta, suppose theta was positive here. Had there been some matter, it could have compensated and become zero.
Yeah.
But you can do something on one side that removes all that matter. And so if it was positive here, it would be positive thereby.
Yeah. That's it.
And so the key point is somehow that you can remove that matter
Yes.
in a way that doesn't.
Yeah, exactly. It's like basically we just boost it up.
So this quantum cycle cannot be defined with respect to boundary just simply by taking those density matrices on the boundary.
That will do a different thing.
So what will you do in the bulk?
That will create. So we only know the bulk action of the boundaries is if you're assuming quantum extremality, which where what it will do is it will create a shock. It will create a you basically put a sort of shock in the initial data on this null surface. Okay, a sort of shock. In higher dimensions, it's a Y shock. In JT gravity, I haven't worked it.
But that's not enough for what you are doing.
But that assumes quantum extremality.
Oh, okay.
I want to get to extremality. I don't want to put it in.
And sorry, Ronak, you had this boosting effect, but you also had this creation of these two shocks.
That's the quantum part of quantum extremality.
That is that?
That gives you the quantum. The boostingness gives you extremality. The shocks give you quantum. Like if I could have forgotten about the shocks and put small thetas everywhere and remove the Q here and the argument would have gone.
The thing I wanted to understand was that the boosting takes what your original state to almost vacuum, but almost vacuum with this shock.
Yeah.
That doesn't change anything.
That is important to basically that's important to remove the quantum part of the quantum expansion.
Okay.
Okay, so what happens is that the derivative of the entanglement gets compensated by a stress tensor shock. Okay, they're cancelling between each other.
Those are important for matching the Israeli time in the presence of non-matching.
Maybe some quantum is like if you just take the classical subversion of CD flow, just boosting the thing away, then you should still satisfy the conditions.
Sure.
And what happens is Z junction conditions, the classical expansion can jump by an amount equal to the shock thing, and basically if the shock is zero, then the classical expansion continues. And you only get classical extremality. What happens here now with the shocks is that you have quantum expansion here, that becomes a classical expansion here, and then you just
That's what I'm saying. So the shock exactly makes the
yeah. Anyway, so yeah.
Classical version is just you don't have the matter crossing that way.
Send it off.
Yeah, you boost it
off is a bit mysterious.
Okay.
No, I'm boosting it away because like it's kind of a smooth process. I can deform it to the identity of it. Right? Boosting is nicer that way. Whereas like if you just said, okay, I will remove the shocks, remove the matter crossing, it might be like, okay, there might be some loophole there. Boosting is some smooth.
It's another classical solution, right? In the end.
Yeah,
These
in the
are
end,
classical
yeah.
statements, so there's one and there's another.
Yeah, in the
And
end, that's
the
what.
other is obtained, even though it's classical, I think of it as some classical version of the unitary transform.
Yeah, it's very much a unity. Yeah.
And that's sort of somehow
I think that's exactly right.
And it's important that you're doing it only from one side.
one side.
Yeah.
That is somehow the key.
That is so key.
Yes.
Yeah. Because one side in the argument, one side is the thing where I want reconstruction, the other side is the adversary, which is trying to break my reconstruction by acting with these units. Okay, good. So now, so the point is that the only remaining candidates for the sub duals are the wedges bounded to external surfaces. Now, there could be that some of them are inconsistent for other reasons, but right now I have reduced it to a finite set of candidates in generic. Okay. The complementary recovery assumptions are important, and without it, what you get is that you can prove this thing as long as the general entropy decreases under output deformations. Okay. Or if it increases under output deformations, which are some of the counter examples you guys actually already thought of, then you cannot prove it without complementary. Islands I will skip. So just to say what I found, we found that in GT gravity CFT with a nice semi-classical order of limits, the statement that little b and little b bar are the EWs of B is inconsistent with boundary causality unless the boundary of B is a quantum mechanical surface.
And the fact that it should be minimum doesn't get come out.
Then not.
That's the island part. Then.
No, that's not the island part. I will get to it's 120. How much discussion should I do?
We have lunch, right?
Yes.
Okay.
To go out for lunch.
Can you give me an hour cutoff?
Eat 10 minutes.
Okay, cool. So let me first tell you the really cool thing. Okay. So the CCW thing, I still do. I have no clue how this works, but it's barely true. The CCW condition. Okay. So let me.
That was the most obvious part of it.
Yeah, but it's like it almost fails. It almost fails. Okay, it's kind of crazy. So what have we done? Okay, suppose there is an operator dressed to B bar, which is this line. This line is addressing, and you have an operator close to the horizon here. What we found is that the commutator of this of these two operators in the state u prime psi is not 0. Okay, unless if B is not extreme. Okay. Because basically this operator does to B bar and B bar moves up, this operator also does it. Okay. But as if you assume that A and U prime commute, okay, this is just a statement that A and the commutator of A with U prime dagger A prime U prime is not 0. Okay. But then the point is that this guy, okay, U prime has large back reaction. But U prime, A prime, U prime dagger, this guy is just moving A prime in along some local flow. That doesn't have a large back reaction because A prime did not have large back reaction. In other words, you are removing the back reaction of U by adding a U prime dagger. So now this guy is 0 up to exponential corrections, assuming U prime actually lives in the complement of the system. Okay. But we found that that's not true. Okay. Which suggests that this U prime, this assumption 3 almost fails. It's like if it only works for extremal surfaces. Okay, and that was what made the proof what made the argument possible. Okay, that U prime would not exist as an operator on purely the right side unless B is an extremal surface. Okay, so I would love to see this like from some concrete calculation where you try to trace U prime and like it just fails or something. Like if I take B to be, not an extremal surface, but like dou phi equals 2. Okay, that's also a reasonable surface to consider. Tracing to that surface should also work, but somehow it doesn't work. That's something nasty. Okay, it's in a completely non-obvious way. So, yeah, so this might be pointed at taking that tracing to a non-extremal surface might be inconsistent with constraints. Okay, what I used was basically a constraint on a null surface.
I thought you were dressing to one or the other boundary.
No, but like,
I'm a bit confused by the words, I'm sorry.
Maybe, whatever. Dressing to stay to the right of a non-extremal surface in whatever way seems to not work. Okay. But yeah.
You mean if you try to do, I don't know this Conco cycle, but if you try to do something like that, and to begin with, the shock wave you were trying to boost away was not an extremal surface, was not emanating from the extremal surface, then you wouldn't have been able to.
You can forget about the Conco cycle. Just think about like a nice unitary which acts like a boost on the matter field.
Okay.
And just think of an object like that.
You say it's unlikely to be able to dress it entirely to the.
Yeah, somehow whatever what it's indicating that any dressing you try to put over that unitary will leak into this side unless this point is extreme. Okay, and I have as yet been unable to come up with a way to check this using a
But
quantifier.
does this mean that this could have been a proof of what wanted to?
No, the violation of CCW is this contradiction. I'm just reframing the contradiction.
No, I mean, that was an assumption and you wanted to show that that's a.
Oh, if you assume this statement,
CCW is assumed, right? In your previous proof.
yeah, if you assume this, then it follows, yeah.
So this could substitute as proof.
If you with a different set of
Just trying to
assumptions,
get it, huh?
with a different set of assumptions, you would have to assume that U prime cannot be dressed to stay on one side. If U prime can be dressed to stay on one side,
But that was also an assumption of your previous proof.
yeah. Yeah.
CCW was assumption, the fact that you prime.
But I assume U prime can be dressed only for the complement of the entanglement, not for arbitrary. Okay, I didn't make any assumption about arbitrary. This thing is falling out for arbitrary. Yeah, I agree. You probably rejigger the assumptions in some way, but so right now this is something for a statement about non-extremal wedges is falling out, which is kind of mysterious to me. I have spent some time thinking about how to make it said, and I have not or concrete maybe, and I don't know yet how to do it. But this is a very interesting thing that came. Good. In higher dimensions, the audience already kind of guessed. Basically, you want a version of the SSPU reconstruction, but where you allow for our boundary unities on the other side. Okay, and then you basically want to just say, okay, there is some initial data on a null surface which violates CCW, and then connect it. Extremality and focusing. I want to do. Now, how close are we to derivation of QES formula? Let me just put some points. So, basic point is that we construct a situation like this where where the boundary of the dual subregion is to the part like it's basically the future horizon of a subregion, a bulk subregion is the future horizon of a boundary region. Okay. And this is exactly the situation where you can use, after this, you can go back to perturbative things and use type 2 argument to argue that the areas determine the entanglement. Okay. So you get that areas done up, but you still don't have minimality. Okay. And this is where like this paper about quantum approximate error correction might be useful, and I'm still not entirely like. Yeah, I have to make this slide precise, but the idea is that this paper was able to prove minimality in quantum parameter words, but not extremality. And the idea is that gravity gives you extremality. So here, so you minimize only amount, like you report subregions that these guys use would only be regions bounded by extremal surfaces, and then among them, the proof here would give you minimality. So I am not, but there is some issues where like their area is a number, but that won't work in gravity. So summary, again, in GT relative CFT, the statement that little b and little b bar are the entanglement wedges of capital B bar is inconsistent with boundary causality unless the boundary of little b is a QES. And there might be other stuff, it may generalize and to lead to new proofs of QES, but I have not done it.
Any quick questions?
I want to ask this because then I'll ask you later, not so. I thought there were great claims made by Engelhardt and Wall on that the region within the QES would be reconstructed on the appropriate side of the map. I mean, so then if that's true, the entanglement wedge is.
But I'm trying to give a different logic, right?
But is there an absolutely solid proof of that fact?
Not an absolutely solid proof, no.
So
The way the current proof works is following, okay?
It's regarded as gospel truth now.
Yeah,
All the younger people.
But let me tell you, let me tell you as I understand what literature is, okay? You use the Euclidean path integral, Long-Lukowicz, to give you JLMS formula for the entanglement wedge. Okay. Then you apply Harlow and various generalizations, which include like generalizations to type 3 bulk algebras and type 3 boundary algebra also. To then say that subregion duality implies like what do you say? RT formula. And say subregion duality and RT formula are the same. Right. To say JLMS implies subregion duality, so we are focusing on that. And that is where it is. So you have to at some point like take input from gravity, which is the JLMS formula, and then go and talk about abstract QE6. Okay.
So the JLMS is at one loop.
That's a great question. Have you ever thought about it as at high loops? I don't know. Oh no, it is at
All orders, right?
Well, there are some things that are.
Yeah, I think that's
Definitely true at one loop, but in higher loops,
Yeah.
the surface.
Because this is surface fluctuating.
at higher loops. What you can say is that if the bulk relative entropy is 0, then the boundary relative entropy is 0. At all orders.
This has been explained to me many times, but at least I see the replica trick as well. Okay.
So all let's say one. But this curious formula is somehow believed to be some exact formula, right?
QS formula has been proved at all orders of partition theory in the sort of limit that we were talking about earlier. Okay. So
QES is what? QES.
quantum extremal surface.
Which means what?
It's the quantum expansion, the sum of classical expansion and derivative entanglement has to be 0.
At all orders, but then you need to know what the graviton entropy is at all orders. So how can all orders?
But what you're doing is again you're taking the limit where CG Newton
If you have to quantum field theory and
Oh, that sense.
Yeah, but you have some gravitational effects, but not gravitons. Okay, so this is that. So that is not at all orders. What you do know at all orders is that if the bulk relative entropy is 0, then the boundary relative entropy is 0 up to exponentially small fractions. Okay, so this is the all order statement which gives you
In the last thing, if the bulk
Relevant
entropy is
0, then the boundary relative entropy is exponentially small.
No, but in order to talk about bulk, there are subtleties, right? To all orders.
No, CG Newton is much bigger than 0.
Again,
basically
just-
graphical bulk, classically
I
graphical
thought
quantum field.
That's the context in which all
Yeah.
of these things are.
Not quantum gravity.
So it's nothing beyond that. Even the Wall-Engel theorem is not beyond.
No.
Oh, then I don't know.
But there has been some recent progress by
It's stated usually more strongly. Maybe I'm wrong.
there are
Including Xi Dong in his talk extremes.
Yeah, famous talk at straight.
Yeah, ridiculous things.
I think the way you can sort of derive these particulars, you should correct me, is using the generalization of Lukowitz-Malesina to the semi-classical setting. Semi-classical gravity works in this setting.
Yeah, no, but it's true that they also so
I thought this was supposed to be true even at
Okay. So let me tell you. So what they do is they think of graviton fluctuations as being like graviton fluctuations on a classical background. Okay, and then they think of regions in the classical manifold. Okay, and then but there are some subtleties that have not been worked out, but there are some arguments that especially there's a recent paper from Colin Ellerian and Jeff Pennington, which does say something more explicit about that. But I think it's more precise when CG Newton is big compared to D Newton. Okay. Yeah. And if you read Dong and Lukowitz, they're very clear about the limits of the the talks are talks, but papers are very clearly written.
Is the converse statement also can be said? The
What the
converse, if we know about this if the relative entropy in the bulk is 0, can we say about that?
That is the statement we can prove using Euclidean path method. That bulk relative entropy is 0. Okay, at all orders implies boundary relative entropy is exponentially small, which is enough for subregion duality actually. That is there's a paper by Chen and Pennington in 2019 or 20, which shows that this is completely enough.
So to higher order in G Newton, nothing is known or nothing is expected.
It's expected and it's only recently starting to become
You know,
expected.
JLMS gives some criterion,
Yeah.
which if you can implement it in some clear ways,
Yeah.
is
Becomes a proposal.
Yeah.
becomes a proposal and then.
Yeah.
But
Hey, Dong and Nico just worth reading. Like I'm not able to reproduce precise statement, but they have precise statement. They're not like messing around.
Okay, let's sign off.